Dormito bene? Io sì, sì. Anche alla grande. No, no. Poco ma bene. If okay, if you need a certificate of attendance, please ask to the desk. Okay, before leaving. So I think we can start the third day, the last one.
Okay, I'm glad to see that so many persons are here after yesterday's dinner, and after dinner they took quite a toll on us. But I think it's time to begin. Otherwise, we will be too late for the remaining sessions. And I will introduce my colleague that will introduce Professor Walter Beek, that will give us the Lectio Magistralis for this workshop. He doesn't like to being called a professor, but it's a professor ad honorem, so it's quite a good thing to remind it. Okay?
Young professor.
Very young professor, and okay, he's eager to give private lessons to pretty girls here around, so.
He's still drunk.
So I think a lot of you enjoyed the social dinner. The one that enjoyed the more, I think they are still sleeping because, and so now, unfortunately for them, you are awake, you are here, and so I can introduce you a renowned scientist that worked a very long time in the maintenance of the national standard of mass, and the polisher. And I don't want to steal time because I think this is a very interesting moment because as you can see, if we switch to the presentation and we switch to full screen, I think it's this one. Okay, metrology, why not? It's an intriguing title, and I think a lot of you, like me, when I came here the first times, I heard about the connection, the often unknown connection between physics and metrology, and vice versa. So, Walter Beek, please.
Many thanks, but I'm afraid the title is something just to attract you, but metrology is a boring activity. There is nothing to say. So. I apologize in advance because I also had last night some entertainment, so I'm quite sleepy, so I will try to do my best. It's nice that the young organizers of a young meeting of young scientists thought to an old retired for the Lectio Magistralis. So I'm grateful. And I hope that something will remain in your minds. So, metrology, why not? The title comes from this. This is the front of a very old paper. Very old means 40 years, 35. Pierre Jacomo was one of the historical directors of the BIPM, the Bureau International des Poids et Mesures. I will explain you what it is. And this was the title of, you know, those paper people write when they become old and they don't know any longer what to say, a little bit like me. And so he entitled, Pourquoi la métrologie? And a colleague of mine noted here, Pourquoi pas? So why metrology? Why not? This is the inspiration for the title of my talk. Well, metrology, you see, this is, most of this is taken from Wikipedia. So this is some Egyptian god weighing. Pay attention to the difference between weighing and weighting. Weighing the heart of the dead, presumably with respect to some standard of the time. Okay? So this is just to say, metrology is a recent name for a prior name which still remains weights and measures. I discovered, after some years working in this field, that weights and measures is, if you look at it, it is a funny weight. and measures. What is measure is a generic term. You think it is a generic term, while weight is a specific. This is not true, because measure in this case means a capacity measure, a measure of volume, because the beginning of metrology was, as usual, for money reasons. You know, there are two things that move the world. One is money. And so a way to decide how much money should pass from one hand to another when exchanging goods was either to weigh the good or to determine its volume, an indirect way for weighing. Okay? So weights, balance, and volume, measure. Okay? So this is the origin. So this is the very beginning of metrology. And so you can find that. But slowly, in centuries, metrology organized into three main disciplines: legal metrology, scientific metrology, and applied or industrial metrology. Let me give you some historical trace concerning this. 1851 to 1857, great exhibitions in London and Paris. In 1867, they created in Paris a committee for weights and measures and money. This confirms what I said just earlier. 67, sorry. Second World Congress of the International Union of Geodesy and Geophysics. 69, French initiative. French people wanted to rationalize. You know, they had Descartes, and so they wanted to have a rational word, the decimal system and so on. 1870, but the Franco-Prussian War in those years slowed down the process. So the first effective meeting was in 72. 40 recommendations, imagine. 40 recommendations. 20th of May 1875, the Meta Convention. This is the second oldest international treaty between countries. 20 participants, 17 signatories, among which Costantino Nigra, Minister of Italy. Okay, 1889. We will have no time for seeing that, but the Meta Convention, the signatories of the Meta Convention had some advantages. They had to pay, and it is still like that. Italy each year pays something like 650,000 euros to the BIPM to honor the Meta Convention. And you have something in change, of course. You had, in 1889, 2 copies of the prototype kilogram, that is the number 5 and the number 19, I think, which are still kept in Rome, unused. Those that are used are here. And if I have time, I will explain you that. And you get a copy of the Meta, and you get assurance that whenever you need to calibrate them, you can give them to the BIPM, have a calibration, and have them back with a value and possibly an uncertainty. Okay? In 21, they made some minor modifications to the convention, and in 1999, so this is at last in our era, the mutual recognition arrangement. We will talk about all that, more or less. Meta Convention. UK didn't sign the first time, but they did in 1884, just in time to receive the copies of the prototypes. They realized lately that there were some advantages. The main outcome of the Meta Convention was the creation of 3 international bodies. The Bureau International des Poids et Mesures, Bureau is office, but it is a laboratory in itself, BIPM. the General Conference on Weights and Measures and the International Committee for Weights and Measures. Acronyms is CGPM for the General Conference, CIPM for Weights and Measure. Okay. From the original 17, let's say 18 with UK, now there are 58 member states in 2016, and there are as well 41 associate states and economies. Associate means that you pay less and you have less privileges. This is the list of the member states. I didn't put the associates. The General Conference. The General Conference is something at the diplomatic level. So when they want to hold the General Conference, they write to the governments, okay, and not to some research institute. And so who goes there is a delegate of, in a sense, a plenipotentiary of its government, okay? This does not happen with Italy because you never have full power of deciding. You always have to ask your ministry. The ministry does not reply to be on the safe side, and so on, but this is Italy. So you have delegates. Typical delegation is 2-3 people, okay? Directors of NMI. NMI means National Metrology Institute. We'll see that also. The General Conference meets every 4 years, more or less. It's a big thing to organize. They meet in Paris or in Versailles, but anyway, there. The last meeting has been in November 2014. The next meeting is marked in red because it will be a very important one, and we will see the reason. The General Conference will receive the reports, but the most important thing is that it accepts or endorses the recommendations submitted by the International Committee, the CIPM, which in turn are the expression of the metrological community. So in 2018, probably, the new international system of units will be established, and this will be based on a recommendation by the CIPM and so on and so on. The second important thing is that it approves the budget of the International Bureau for the following 4 years. Okay, it's a funny thing is that they need unanimity. They need unanimity, and if not, in the negative, they must hold a totally new conference. So the United States, which always have this kind of attitude towards international organizations, think about the United Nations and so on, always abstain in the first rotation, just to say, okay, we let this organization to exist, but just to be clear that who rules is the United States. And in the second rotation, typically accept, okay? So this is the point. The International Committee is something made of men, or women, of course, humans, okay? I tend to be not politically correct, so excuse me, I hope not to offend anybody. It is made of 18 persons, coming from the most different parts. Typically, in the last years especially, they are directors or high-level staff of some National Metrology Institute, but not necessarily. Okay, they meet annually. Actually, they meet twice per year, informally, and discuss. They are really the sort of board of control over the activity of the International Bureau. Okay. Normally, the members of the CIPM are also presidents of the consultative committee. We will see what are the consultative committees. Just to give you an idea of first idea of the interconnection between physics and metrology, look at the names here. We have 5 Nobel Prize winners: Louis de Broglie, sorry, or de Broglie, I never understood, Michelson, Zygmunt, his son, because genius is something which is inherited, typically, and Zeman. So this is something made of strong guys, typically, not necessarily. Other notable people are, I don't know most of them, but Darboux tells me something. Fabry tells me something. Galileo Ferraris tells me much, because the INRiM, one of the two parts of INRiM previously was entitled to this engineer, physicist, engineer. This tells me a lot, Fredholm, integral equations. This is somebody, Mendeleev. Vito Voltaire is somebody. And so these are notable people who, in different times, belonged to the International Committee on Weights and Measures. Okay? So it might be boring, but other duties, we skip them. Now we come to the International Bureau. The International Bureau is a building with people inside. Okay? So the General Conference is a conference. It does not exist typically. It is established every 4 years. The CIPM is a committee, and the BIPM is a building with people working in it. It is in Sèvres, in a very beautiful place. It is a good thing to be a metrologist, just to have the opportunity to go there from time to time. The people into there are considered, well, it is an international ground, so they have some privileges also. The budget is 13 million euros, so not very much compared to ours. Ours might be 25, 30, I don't know. So it is a comparatively small institute. It is financed by, as I told you, the signatories of the Meta Convention. The countries pay according to their size. So when in the past we were proud of being among the first 5 industrialized countries, that we had to pay more. And so they are more or less 70. They were recently reorganized. They have a physical metrology time. Physical metrology means electricity and mass, basically. And then they have time, ionizing radiation, and chemistry. They are not afraid of closing some sections when the conditions impose that. And this is the spot. I go there from time to time, twice per year actually, and we meet somewhere into there. It is not too bad. The mandate of the BIPM is to provide the basis for a single coherent system of measurements throughout the world, traceable to the SI. That means they calibrate standards for people asking, not for people, for countries. They coordinate through comparisons. They maintain this key comparison database, and they are becoming more and more a conference center because there is an innumerable number of events every year. The CIPM, the consultative, the International Committee, has established a number of consultative committees, and here is where people coming from the various countries, from here, from France, from whenever, go and contribute. And these committees have the task to consider the advances in physics that influence directly metrology, preparation of recommendations, we will see, advice to the CIPM, and so on and so on. They meet when needed, not necessarily. They have not frequency. The president is a member of the CIPM, typically, and the members of the committees are institutions. They are not people. So INRiM is member of that and this and that committee. And each time a delegate is sent by INRiM. This is the list. Acoustics, ultrasound and vibration. Electricity and magnetism, you see when the dates the dates of establishment, length, mass and related quantities, photometry and radiometry, amount of substance, that is chemistry, ionizing radiation. This has three very different subcommittees. Thermometry, yes, time and frequency, and then we have more. And this is, these times, the most important by far, the consultative committee for units. And this is the steering committee behind the redefinition, the change in the SI. Okay. This is just an example. Each committee has working groups. So the CCM, that for mass, for example, has density and viscosity, free flow, force, and gravimetry, and so on. Okay. This is just to show you how inflection works. This was the first meeting of the CCU, that for units, and this is the latest one. So you see, there is room for everybody in metrology. Okay. Joint committees, there is a number of joint committees. That means that they are made by the metrological organization, BIPM, CIPM, and so on, and other organizations. For example, I operate in this one, JCGM, for guides in metrology, and in this committee sit a lot of international organizations. National metrology institutes, familiarly known as NMIs. The model is the Physikalische und Technische Reichsanstalt der Bundesanstalt, 1887. Funnily, the United States didn't come first. Then we had the NPL, and then we had the NBS, now NIST. Okay. Okay, the missions are different. Of course, NIST can work on a very wide spectrum as PTB or NPL, from support to industry to advanced research. They have 3 Nobel laureates working currently into there, and so on and so on. A small laboratory such as that of El Salvador, just to mention one I know, has 4 people doing some calibrations and nothing else. But in principle, they all sit with the main. It's like a bit like the Football Federation. You have small countries and big countries sitting in the at the same table. This is more or less the structure of the whole thing. Okay. Then we have the regional metrology organizations. So we have for Europe, which was the first, and this is a good lesson of how things happen for irrational reasons. That Euramet was born as a response to an attempt of a specific laboratory of the European Commission, the GREL laboratory, to become the metrology laboratory of Europe. So bypassing all the national laboratories at that time, you know. We had United Europe and so on. So this laboratory raised its hand and said we could act as European metrology laboratory. The immediate response, imagine PTB, NPL, INRiM also at the time, the 2 institutes at that time. We are a unique institute of metrology, almost unique. Just since 2006, because before we had 3 separate laboratories. Now we are 2. So the reply was impossible. But the European Commission said, okay, impossible, but do something to coordinate your work. Otherwise, it would be possible at your expenses. And so this Euramet was born. Euramet was born, and of course, if there exists one, the others feel obliged to do the same. So we have this proliferation of regional metrology organizations. They are structured like you have a general assembly, main board, and so on and so on. Our scientific director is the vice chairman or chairperson of Euramet. This is the structure. For example, this one, which is large, This is Sistema Interamericano de Metrología. They use Spanish because Spanish is more widespread than English in this continent. Think about that. So if you need to survive somewhere, perhaps Spanish is better than English. Okay? Okay, so MRA, and we are almost at the end of this part. Mutual recognition arrangement. The BIP, this is my malicious interpretation. The BIPM experience in the last years decreasing of its importance and influence in the international landscape of metrology. So at that time director, Terry Quinn, devised a very clever mechanism to ensure its perpetuity. So this mutual recognition arrangement. Just as an anecdote, arrangement was compromised because the original formulation was agreement, but the United States declared that agreement was too demanding for them, so it was changed to arrangement. Don't ask me the difference, but there seems to be a very important difference. So now we are 102 institutes and 165 designated by the signatory body. Designated means that if you are a national metrology institute and you are unable to do some activity, for example, calibrating flow rate meters up to 100 cubic meters per minute, for example, you designate somebody else able to do that for you. Okay. The objectives is to establish the degree of equivalence. We have a complex net of secondary labs, and we ask them to demonstrate their capacity by showing us a quality system, procedures, and checking their ability with calibrations and so on and so on. The same was asked to National Metrology Institute. This is the essence of the MRA. Okay, so there is a lot of comparisons of standards. You circulate a standard, everybody weighs it, or compares it, or calibrates it, and then you compare the results. A lot of statistics, and I am sorry that I will have no time to speak to you about some interesting things in statistics, such as the use and abuse of the p-value and things of that kind. No time for doing that. Okay, let's go on. Legal metrology. This is the last branch. It was established because the CAPM didn't recognize the need for such an activity. So they founded an independent structure, similar to the one concerning scientific metrology. The name is OIML, Organisation Internationale de Métrologie Légale. You see the member states, General Conference, International Committee. But they issue, they print the recommendations on calibration of weight scales and so on, calibration of glass, and they typically become European regulations. So typically become mandatory in the States. So there is an intertwining between legal and scientific metrology. In fact, in serious countries, the legal metrology and the scientific metrology are operated by the same National Metrology Institute. This happens in the United States, this happens in Germany, this happens in Switzerland. In Switzerland, the Metrology Institute is under the Ministry of Justice. And this shows you, and that was the same in Brazil until some years ago. So just to show you that metrology has also a social need, because if they get me drunk, I want to know if the ethylometer had been calibrated and properly. So I need that. And also, imagine to the needs in clinical chemistry, when they count platelets or whatever. You want to know that these measurements are reliable. So this should be the task of metrology also, not only counting particles or things of that kind. Okay. You can go on this site, the BIPM, and you find more or less what I told you. And then we have a number of other international organizations. ISO, IEC, they are standardizations. IUPAP is the one to which most of you probably sooner or later will belong. The same for chemistry. This is calibration. This is, I like that because that means that they are starting to understand that also in clinical chemistry or in medicine you need reliable measurements, okay? And, oh, I put one, two, twice. Commission Internationale de l'Éclairage is something with the important interaction in connection with the candela, one of the 7 base units of DSI. And then this is, at this moment, the most important. Committee on Data for Science and Technology, and especially the task group on fundamental constants. I told about that. Okay, this is the end of the boring part, I hope. Now we open a small this is the structure of metrology, okay, the boring face of metrology. This guy was awarded 2 or 3 weeks ago the Nobel Prize for Physics for some exotic interpretation of some states of matter in terms of topological properties. But he was very well known in Torino here because he used to be a climber, an alpinist. Mike Kosterlitz, this is when he was young. All this was found on Wikipedia, of course, but and this is some years ago. And he is the guy in action somewhere in Welsh, sorry. What is funny is that he went to Torino in '72, I think. I never met him. I never met him because I was younger. Seems impossible, but I was younger. And he was, I don't know whether at physics, university faculty department of the university or at the Polytechnical School here. But he went here presumably for a postdoc, something of that kind. And since he was a climber, he went to the alpinistic environment here, the ambient. He went to the Alpine Club and asked to tie himself to the rope of somebody for doing some climbing. And you know, here people are very diffident, so it is not necessary that you come from England for being a stranger. It's sufficient to come from some place 20 kilometers away. So the community was a little bit diffident. When they discovered that he had already climbed some very difficult routes along the Alps, not only here but also in the Dolomites and so on, they were more. So they established a relationship, especially with 2 or 3 of the local community. And which was the surprise? The surprise was that he imported a totally new way of climbing, because he was master in the technique of crack climbing, okay? Because that was a technique which here was non-existent. Nobody knew that way of, you simply lock your arms or your leg or your hand into the crack and you can climb even if you have no places where to hang. And so he managed to climb free pitches that were impossible for the local people. So he left really an imprint in the way of going to the mountain here in Torino. He opened things like this one. This is Pizzo Badile, just to say. And this is a crack. And it is known as the Kosterlitz crack. And he opened that, the first, in 72 or 74. And it is in Ceresole, so some 60 kilometers from here. And the first guy who managed to repeat the climb, this is, as you can see, it might be 6 meters or 7. The first guy who managed to repeat this climb did that 8 years later. So they attempted for 8 years. So you say, okay, it was a physicist, but he was mostly a climber, so probably was not a very good physicist. No, he was a good climber, extremely good climber, and an extremely good physicist. So, and he was not alone in that. There was a precedent, which was Bill Shockley, one of the inventors of the transistor. There is still a Shockley ceiling somewhere in the Utah Mountains or so, which is still a valued passage to climb. And so just to show you that you have this is a little bit frustrating, because if you go to the mountains, as I used to do, and if you are a physicist and you discover that there is a very good climber, which is a physicist, you say, okay, but as a physicist, probably he is nothing. No, he's better than you at climbing and at working. So consider that. Now the second part, the international system of units. Some history again. A unique system of units. In 1788, in France, there were about 2,000 units, among which 200 different livres, that is to say, weight units. Okay. 1789, cahiers de doléances were something established by the king to try to defend himself from the protest from the people, which was growing more and more. And so people were invited to deposit, to write their complaints. Doléance means complaint. There were three categories: people, priests, the clergy, and the nobility. Okay, one of the most frequent complaint was the huge number of different units, because of course if you have a unit for buying and a unit for selling, you can gain. And so the need was felt for unification. Again, money that decided that. So a French law in 1795, but French wanted to internationalize this move. They had the metric system in France on the 1st of January of 1840, and in 1875 they managed to have the meter convention. So they managed. There is an interesting history concerning the determination. You know that the meter was originally defined as the 10 millionth part of 1/4 of the meridian passing from Paris. And they sent for measuring that two people, one aimed north and the other south, and they anticipated that they would be able to report on their measurements within 7 months. And it took 7 years to do that, because in the meantime they wanted to do that, the French committee, because they wanted to have an international thing. So they wanted to cross Spain and England, so that they could say that it was an international effort. But there was a war in the middle, and so on. So it took 7. There is a very interesting book I can show you if you like. Okay, 1960, the International System of Units. This is the 15th anniversary of the international system during a meeting of the CCU. This nice guy is Ian Mills, at that time president of the CCU, with the executive secretary. Precursors to the SI. CGS, centimeter gram second, divided within electrostatic and then electromagnetic system. Then MKS, kilogram second, MKSA, including the electrical units, 1946. The present SI, just to refresh you a little bit, is based on 7 units, for as many quantities: length, mass, time, electric current, thermodynamic temperature, luminous intensity, amount of substance. The last having been introduced in 71. Okay. The units are defined, so there is a sentence saying what is the unit. Okay. These definitions are various in the current SI, and they are based on the historical moment. They reflect the historical moment at which they were established. The oldest are based on an artifact standard. The kilogram is the unit of mass. It is equal to the mass of the international prototype. Stop. So you have an object, and you say, this is the kilogram. You have no realization. You need not realize it, because it is self-realized. It is there. Okay. Then you have, and this is based on an artifact. That was the meter, for example, at the beginning, a bar. So you had to compare. That was the length of the arm of the king in the origin. So this is the beginning. Okay. A small step based on a natural standard. Always a standard, but now natural. The second is the duration of periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state. This is the current definition of the second, but this transition is simply a natural standard. This is not an universal constant or whatever. We know that it is constant, but it is not a constant of nature in the sense of the speed of light or the Planck constant or the Boltzmann constant or the fine structure constant. It is just a natural standard. Okay, so this is the definition. Then you have the third step, definitions based on fundamental constant, and they already exist in the current international system. So the meter is the length of the path traveled by light in vacuum during a time interval of of a second. So this means that you base your definition on the speed of light. Okay. And then there is another instance, which is the ampere, which is not so evident, but if you look at the definition, you realize that the ampere is based on mu0, so on the magnetic constant. Okay. So these are more or less the, okay, this is more or less the kind of classification of the definition. Natural standard, artifact, natural standard, fundamental constant or constant. Base units are conventionally regarded as independent base quantities. Base units are not. These are the interconnections between units. The kilogram is connected with the candela, as singular as with the mole, chemistry. The second is now with the candela, with the ampere, and with the meter. And so the Kelvin is alone. Derived units, we skip that. Just we have a look at this. The radian and steradian are special names for the number 1, because the radian and steradian in the current SI are considered as dimensionless, okay, because they are the ratio of two lengths, radius and an arc, okay. This gives difficulty. We will see in these 5 minutes what happens. There are a number of just mention about notation. I will skip this one, but have a look at it, because you find too many papers in which notation is totally neglected. You can go and which are the areas of improvement of this structure? The structure of the system itself, the stability of the mass unit, the uncertainty of fundamental constants, the situation of electrical units, and the dimensional units. Now we will look a little bit at each of these, and we will see what was done to improve that. The structure is that many of the definitions are circular. So base units are defined in terms of derived units. Look, the second is defined in terms of the hertz, which is its reciprocal. The meter is defined in terms of the second. The ampere is defined in terms of a force, which is a derived unit. So this is some unsatisfactory. something unsatisfactory. Second point, stability of the mass unit. The stability of the mass unit is a problem. This is the national prototype of the kilogram. It is kept in Sèvres for some years until 2018, will remain the mass unit. This is the definition. This is something funny I found, an assumption that the kilogram was stolen, and since the theft, 428 organizations and 328 individuals have made claims that the kilogram in each of their possession is in fact the correct one. So various definitions of the kilogram. The weight of the perspiration generated during a 12-round world title fight at sea level, and then various definitions. It's funny. This is an interesting scheme showing you that, I give you just the essence, the prototype kilogram demonstrably drifts in time. You cannot say that because it is the unit, but you can compare it with its companions, the national prototypes copies, and you see that most of them are relatively stable. They remain more or less, their differences are more or less unchanged, while the prototype changes. So this is, the amount of change has been of more or less 50 micrograms. Look, micro in the kilogram does not mean 1 in 10 to the minus 6, but is 1 in 10 to the minus 9, because there is a kilo in the unit. So 50 micrograms means 5 in 10 to the minus 8 over 130 years. This is the change, more or less, of the prototype, okay? So the first solution was, this is due to nobody knows why, a provisional solution in 92, but the problem is there. Third place of improvement, area of improvement, give me 5 minutes more because we started later, so. The uncertainty of the fundamental constants. Most fundamental constants are experimentally determined in terms of SI units, so they have an uncertainty, okay? And they give a lot of work to people, happily, who spend their career measuring and remeasuring fundamental constants, trying to improve their values, okay? Digression on uncertainty. In this world, nothing can be said to be certain except death and taxes. This is a very famous citation. There are more exceptions. For example, the speed of light was declared conventionally exact in 82, I think, sorry. Electric and magnetic constants, and so on. Just a remark, conventionally exact means that you must imagine an infinite sequence of zeros after the last significant digit, because should it be truncated there, there would be an uncertainty. They are exact, and to be exact, they need to be real numbers. So an infinite sequence of decimals, okay? Remember that. The other constants are uncertain. Even pi, look, pi, we know pi to 10 to the 15 digits now, perhaps when I read that, perhaps now 16. Anyway, a lot of digits. But we don't know which is the next digit. So we know that pi is an irrational number with an infinite number of digits and so on and so on. But we are uncertain about it, okay? So this is the point. We have the symbol. We believe that it has a true value, so to say, but we have an uncertainty of that. So uncertainty arises in connection with incomplete knowledge. I will skip all this part. Now, this is the present situation. I hope that the colors I choose are readable. Not very much. Anyway, we have in the current SI a number of things which are conventionally exact. So the speed of light in vacuum, the mass of the prototype kilogram, the frequency of the hyperfast splitting of cesium, the magnetic constant, the molar mass of carbon-12, the temperature of the triple point of water, and the spectral luminous efficacy, which is something that converts radiating power to subjective. This is connected with the candela, which is a physiological quantity. There is nothing universal in the candela. The candela is based on a sample of 100 people examined some 50 years ago. So, okay. And then there is a number of uncertain things, and these are the Planck constant, the elementary charge, or charge of the electron mass, the Avogadro constant, and the Boltzmann constant. You see that there is something which clashes with common sense and with our beliefs about the way in which nature is structured. We can bet on the speed of light in vacuum. Now, forget a little bit about the theories suggesting that fundamental constants are fluctuating according to the expansion or contraction of the universe. There are tests about that, and you can go and check that to every human conceivable purpose, they can be considered constants, okay? So the speed of light is a constant, and we can bet on that. I wouldn't bet a penny on the mass of the prototype kilogram being constant over time. This is a constant, probably. Magnetic constant, we believe that it is something which does not change. The same applies to the molar mass of carbon-12. This is not true for the temperature, the triple point of water, because there is evidence that this is not a stable quantity. And this is even, and at the same time, we are ready to bet on the constancy of the Planck constant, of the elementary charge, of the electron rest mass, and so on. So there is something in the present structure of the SI that clashes with our knowledge or our belief about nature. Okay. Now, situation of the electrical units. I told you that these were the areas of possible improvement of the SI. The volt of the ohm and the ohm are nowadays represented in a highly reproducible way by means of Josephson and quantum Hall standards, depending on the Josephson constant and the von Klitzing constant. These two constants enable a consistency worldwide, which is much better of that you would have should you realize literally these two quantities in terms of the ampere, which is the prescription coming from the SI. Okay, the point is that these are reproducible, and but they are written in terms of the electron charge and of H. And since these have an uncertainty, also they have an uncertainty. This is Klaus von Klitzing, the discoverer of his constant, and this is Brian Josephson. So the two constants have an uncertainty in SI units, okay? And in addition, what electricians, metrologists use now are not these values, but are conventional values which are considered exact. This is the reference publication concerning everything on fundamental constants, okay? Now, the last area of unsatisfaction is that of dimensionless units. So you can write the SI unit of frequency is given as the hertz, implying the unit cycles per second. This is from the brochure of the current SI. So 1 hertz is 1 cycle per second. Everywhere in the world, 1 cycle is considered as synonym for 1 revolution. So 1 revolution becomes 2 pi radian per second. Since you can omit the radian, because the radian is a special name for 1, okay, you have that according to the rules of the SI, the hertz is either the reciprocal second or 2 pi per second. So this is an ambiguity. This was raised not by me, but by Bill Phillips, which is another Nobel Prize winner, okay? And this was accepted in a very skeptical way by the community, but I am deeply persuaded that they are right and that something should be done here, okay? A similar problem you have when you have to count, count rates and things of that kind. Now, improvements. kilogram. This is an early proposal dated 63 by Claudia Gidi, who was in the past president of this institute. And then in 2005 we had the bomb. They proposed to redefine the kilogram in terms of the Planck constant. These are the authors. They are all big guys of our community, okay? And then in 2006 they continued by suggesting not only to change the definition of the kilogram in terms of the Planck constant, but also to change the definition of other 3 units, that is the ampere, the mole, and the Kelvin, okay, in terms of as many other universal constants, okay? That was the proposal. The 23rd General Conference endorsed this view and said, okay, go on that. The proposal means reorganize the uncertainties in that table I showed you earlier and assign conventionally exact values to a number of suitable constants, okay, and define the units in terms of those constants, okay. So redefinition of the almost all of the 7 base units. Which values to be chosen for the constants? Those recommended by the CODATA, which is the task group I told you. This task group spends their time to look at the experiments done throughout the world and to examine their compatibility and to find a way to combine the experiments concerning the same unit, the same constant, to combine them into one recommended value. So whoever needs that goes there and has a recommended value, okay? These are the invariants proposed. So the speed of light for the length meter, and it is already like that. The Planck constant for the kilogram, and this is one of the novelties. The cesium frequency for the second, nothing new. The electron charge for the ampere, novelty. The Boltzmann constant for the Kelvin, another novelty, and the Avogadro number for the mole, that is for the amount of substance, with the interconnections between. So this should be compared with the one circular I presented you earlier, and you will see here that there are a number of changes. The mole is now isolated, which is not liked by chemists, and they are perfectly right in not liking this future system from their viewpoint. Now let's have a look at how they measure these constants, a very fast one. The Planck constant is measured using the most accurate measurement using a Watt balance. The Watt balance is a balance in which you have on one side the mass subjected to the gravitational force, and you balance this force using a current flowing in a coil, a current I flowing in a coil of length L within a magnetic field B. Okay, so you measure the current needed to balance that, and this is one of the 2 stages of the experiment. In the second stage, you simply move the balance, the arm at constant speed, okay, through the magnetic field, which is supposed to be the same as before, and you measure the electromotive, the voltage. You measure the voltage. The voltage is a function of the length of the coil, of the velocity, and of the magnetic field. And you measure this voltage in terms of the Josephson and von Klitzing constant. And if you put together a number of equations, you come to this. So you have that the Planck constant is related to the mass through the gravity acceleration, the velocity of the balance of the beam falling down. This is a geometric factor. B and F are geometric factors. Okay, so you have a link between the Planck constant. Look, the Planck constant is a unit of action. The mass is a mass. And this is an old picture of the first NIST balance. The idea came from Brian Kibble, NPL, and the first realization, practical, the first number came from the NIST. Okay, now the current what balances are a tabletop experiment, more or less. The Avogadro constant is measured by the X-ray crystal density experiment. So you have a cell, this is the cell of silicon, and you have a sphere of silicon, monocrystalline silicon, so that you have no vacancies, no imperfections, and so on. You have this formula giving you the Avogadro number or constant in terms of the volume of the sphere, so you need to measure it very thoroughly, of the molar mass of silicon, and this is also a difficult measurement, the volume of the unit lattice cell, and this implies the measurement of the lattice parameter, which is a pride of our institute that was measured here with the highest accuracy. Now the Germans are trying to repeat that measurement. So you have a link between the mass and the Avogadro number. So what should we choose as a constant associated with the mass unit? The Avogadro constant or the Planck constant? Happily, they are related by this formula, in which this is the electron mass, this is the mass of an atom of carbon-12, this is the fine structure constant, this is the Rydberg constant. The point is that these constants, these other constants, are so well known that once you know the Avogadro constant, say, you can claim that you know the Planck constant with almost the same uncertainty. Okay, so you can compare experiments coming from both ways, the crystal density and the Planck constant. This is the point. So measuring either of the two constants is equally good for determining the value of the other constant. This is a graphic of this is taken from, again, from the CODATA publication. You can see the consistency. Of course, what weights in the adjustment are the things with the smaller uncertainty. So this is Avogadro 2011. This is Avogadro 2015. This is the NIST balance. This is the NRC balance. This is a preliminary result. This is the CODATA value, very small. Boltzmann constant, I will skip that. There is a way to measure it. That was the compatibility. This is the future scenario. The future scenario is speed of light, still exact. Mass of the prototype kilogram, sorry for that means less than 2 × 10⁻⁸. So the prototype kilogram will take an uncertainty. The magnetic constant will take an uncertainty. The molar mass of carbon-12 will take an uncertainty. The temperature of the triple point of water will again. The spectral luminous efficacy will not move. The Planck constant will become exact. The elementary charge exact, the Avogadro constant exact, and the same for the Boltzmann constant. Okay? So we have reorganized the uncertainties in the fundamental constants. Okay? Implications. The two von Klitzing and Josephson constants become exact, which is an advantage for electrical metrology. Now they can claim that they are giving measurements in terms of SI units, which was not true since 1990 on. But mu0 and epsilon0 and zeta0 would take an uncertainty, of course. You cannot have them all without uncertainty. The mass of the prototype will take an uncertainty, and the temperature, the triple point of water also. And this is good, because we don't believe that they are stable, okay? And also the molar mass of carbon-12 will take an uncertainty, which is not that good for chemists. Not from the practical viewpoint, but from the conceptual viewpoint. The future formulation will be that the International System of Units, the SI, is the system of units in which these 7 constants have these values in SI units. This would be sufficient to define everything. You no longer need base and derived units, because these are the base invariants, so to say. They are not all constant, fundamental constants. That's why periodically they call them invariants, because this one has nothing to do with fundamental constants. Okay, but that would be sufficient to define all the units, the current base and the current derived. The distinction will be kept for historical reasons, but there is no scientific reason to keep a distinction between base and derived units. Okay, the format of the definition is this one. The second is the SI unit of. There is a problem. The problem is that the constants belong to a set of quantities, and the units belong to a different set of quantities. An example: the kilogram is a unit of mass, and it is defined in terms of the Planck constant, which is a unit of action. So it is difficult to describe how the kilogram is defined in terms of a different quantity. Okay. The point is that with the 7 constants, you can always, of course, form a monomial expression having the dimension of the quantity of which you want to define the unit. So with the Planck constant, let's go to the second one. The kilogram, symbol blah, 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 is the SI unit of mass. It is defined by taking the fixed numerical value of the Planck constant to be blah, 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 when expressed in the unit blah, blah, which is equal to, where the meter and the second are defined in terms of. They did not resolve all the structural problems of the SI, because the definitions still need the definitions that come prior to that one. The second is at the base of everything here, and you need the meter is defined in terms of C and the definition of the second, otherwise you won't be able to define the meter. The kilogram is defined in terms of the 2 coming before, and so on and so on. So the structure is not totally resolved. It has improved because the definition have now a common format, but the structure is not perfect. This is the interesting part. You can write that 1 kilogram is equal to 1.4755 something, a monomial combination of the constants, which has the dimension of a mass. Okay? And in this way, you avoid the difficulty of having a constant of some quantity defined. Look at the ampere. The electric charge is a charge. The elementary charge is a charge, and it defines a current. Again, here it is simple because the relation is simply through the second. But this difficulty is everywhere through the new definitions. I would have liked, personally, to see the definition, the kilogram is, bam, where these have the following values. Okay? Look at this exponent, this power, 10 to the 40. Okay? This was questioned by somebody as unphysical. And actually, I think it is larger than the number of atoms in the universe or so. This way of defining brings into light how all units except the mole depend on the second. Okay? All the units depend on the second. And the second is based not on a universal constant, but on a specific natural standard. So a very specific transition between 2 hyperfine states of a specific atom in some conditions. When they will find a better transition, as it's already done because they are moving to the optical transitions, they will need to redefine the second. So, in my view, the definition of the second, the current definition of the second, is not really a definition. It is something that could be used in a mise en pratique. Mise en pratique is a way to practically realize the definition, okay? And in my, not my, another colleague's opinion, the natural invariant, this one, is inadequate as base constant, okay? And this is seen by that exponent to the 40, because this is due entirely to the fact that the definition is based on that transition. The good, in our view, the good quantity to on which to base everything should be the electron mass. So the mass of the electron, of course, you must give up with the transition of cesium. But if you define in terms of the, look at the definition, the kilogram is equal to exactly times 10 to the 30, which is realistic, electron masses. So the problem is that the time and frequency community is not happy with that, because they claim we would lose 3 orders of magnitude. And my reply is, imagine a geolocalization. Now you have more or less an accuracy of 1 meter. And this is based on time measurements. And I don't believe that, should we change that for the electron mass, the accuracy would be degraded by 3 orders of magnitude, so become 1 kilometer. I don't believe that. I'm sure that it would remain absolutely unchanged. There is also an aesthetic reason. You would have the Compton wavelength and the Compton frequency and the mass becoming the reference quantities for length, time, and mass of the same particle, which, in my opinion, has an aesthetic attractivity. Okay. Okay. What about dimensionless units? I was involved in that. There was a party saying, no, if you use properly, if you use properly the quantities and you distinguish carefully between angular frequency, angular velocity, frequency, and so on, there is no problem. But, and these were German, but the pragmatists, that is British and American, said, yes, you should have no problems, but you have problems. So we must solve that. So no consensus was found. The proposal by Bill Phillips, which in my view is splendid, is to consider the Hertz as 2 pi radians per second. And this would imply adding the radian, the angle, as a further base quantity to the system, which has a number of difficulties, but would be a good improvement. So no revision about that. The provisional balance is the structure of the system largely resolved, except the issue of the fact that everything is good, but is based on a standard and not on a constant. Okay? The stability of the mass unit is resolved. The uncertainty of fundamental constants is reorganized in a better way, better reflecting our view of the nature. The situation of electrical units is resolved. The situation of dimensionless unit is unresolved. And I'm coming to an end. These were a number of constraints put by the mass community, essentially, before the redefinition could take place. We wanted a good compatibility, a good consistency of the measurements of the relevant constant, that is of the Planck constant. This now has been fulfilled. This is a roadmap that gives you an idea of how complicated it is to come to the final target, the redefinition. We started there. This is more or less, we are more or less here, okay? And all this was done with some painful times. Then there are meetings, consultation, announcement, and so on. New data for the fundamental constants. Let's hope that no discrepant data come out, because if discrepant data come out, we cannot go on with the redefinition because we want a good agreement. We want to be reasonably sure that the values we conventionally assign are close to the truth. So this is the point, okay? And this is the redefinition, okay. To conclude, and I'm sorry to have, let's say I started 15 minutes late, and I finish 15 minutes, so I'm symmetric at least. Expose yourself to metrology. Thank you. This is a nice guy. He won, I discovered lately that he was the first, the referee, one of the referees of my first game. This is a Canadian. Okay.
So, thank you, Walter. No problem. Do we have any question?
So if you could show again the slide with the measurements of the Planck constant, please, which was the... Because actually the constant depend on the gravity acceleration g, which is everything except a constant. And well, yeah, it depends, actually, the second figure after the comma changes with the latitude and the place and the altitude of the sea level. And, well, actually, there is just one possibility that they could fix that constant, is that they measure the g acceleration in the same place at the same time they measure the Planck constant. That's my... I mean, I was wondering about the precision of this measurement.
A very good remark, but I give you another reason of concern. You are not even sure that the magnetic field is the same when you are in the weighing mode and in the moving mode. Because here you have some iron parts, some metal parts moving through the magnetic field. So there are a lot of problems in these experiments. There is a lot of systematic effects. Little g is measured using absolute gravimeters, and they map with the absolute gravimeter the room of the experiment, and they extrapolate the value with this. But anyway, you put the finger on the right point because little g is one of the critical measurements. It is not a point, the fact that it changes. What matters is that it keeps, you know it very thoroughly at the moment you do the experiment in the same place in which you do the experiment. You're right.
Any question? I have curiosity. Yesterday we went to the Astrophysical Observatory in Pino, and we've been the people there told us about Giovanni Battista Beccaria that was that was involved in the triangulation of the meridian in Turin in the middle of the 1750 or something, and I was wondering if if you remember. I was wondering if there was any connection between his studies and what happened in France, England, and Spain during the triangulation that you told us about. Because he's never mentioned, at the best of my knowledge.
I don't think there is a connection, except for the fact that they were probably establishing an international geodetical net but we are definitely not on the same meridian. So I think there is no connection at all with that. You need to know accurately the position of the observatory if you want to do some astrometry, I think. But there is no connection with the establishment of the meter.
Because the years was
yes, the
time,
time.
so maybe
the time was
completely independent.
Okay. But I don't think so, because the triangulation was along a
Yes.
vertical line,
Okay.
so the meridian. No, I don't think he was involved in that. The two guys of that measurement, I don't remember the name. Delambre et Méchat. One went north, and the other went south. The one to north managed to finish in a reasonable time, I don't know, 1 or 2 years. And the one issued south found a war in Spain. He was kept because he was considered a spy. I don't know whether he had some love story, so it took him 7 years. And finally, eventually, they discovered they had made a mistake. And they had made a mistake so that this did not impede the adoption of their values for the definition of the meter, which shows that some cynicism is needed, some time, and you can establish things also even based on errors or mistakes, provided that they are universally accepted or unknown to anybody. And so that was the story.
Thank you very much. So please thank the speaker again. And now we go on with the first session, regular session of the day. Who's the chairman of this? The chairperson. I'm looking for the chairperson of this session. Full batteries, I think. Okay.
Okay. Let's start with the second session of matter physics with the first speaker, Luisa Mandrile from University of Turin and INRiM, and the surface enhanced Raman scattering exploiting plasmonics physics for chemical sensing.
Okay. Good morning, everyone. I'm Luisa Mandrile, and I'm a PhD student from the University of Turin. But actually, I'm doing my research activity here at the National Institute of Metrology. I work in the Metrology for the Quality of Life division, and in particular in the food metrology program. In this presentation, I will talk about Raman spectroscopy as a valuable tool for food analysis, and I will focus especially on surface-enhanced Raman scattering technique, which is the analytical technique I've actually used for this research. I will show several nanosystems that can be exploited for cells analysis, and also examples of different analytical setups in order to perform surface-enhanced Raman scattering analysis. And then I will give an introduction to a case study which is related to fungicide traces detection directly on fruit. I will show a qualitative in situ approach and two different calibration approaches for quantitative analysis, one monovariate and one multivariate regression. And finally, I will try to give some conclusions. Well, Raman spectroscopy is a vibrational spectroscopy technique which is based on the fact that when a laser, electromagnetic radiation interacts with a sample, part of the photons are inelastically scattered. And the difference in energy between the incident light and the scattered light is a function of molecular vibrations into the sample. So the Raman spectrum can be seen as a molecular fingerprint of our sample because it is strongly related to the molecular composition of the sample, to the chemical composition. For this reason, we can call Raman technique as a fingerprint technology, and this can be a very interesting feature both for food quality assessment and also for food safety assessment. This technique has many other advantages. For example, it is rapid and non-destructive analytical technique, and many samples can be analyzed without any chemical pretreatment. No preprocessing, no extraction, no digestion of samples, and so on. And this is very interesting for process monitoring and also for inline analysis during food processing, or also in-field analysis. It has also some disadvantages which are related most of all to the thermodegradation of the samples under high power laser or fluorescence effect, which is in competition with Raman scattering. We can overcome these problems using low power laser radiations or high wavelength lasers, but this can bring to a relatively low sensitivity. Sensitivity problems related to Raman scattering can be overcome using surface-enhanced Raman scattering technique. This technique is based on the fact that in presence of plasmonically active materials, Raman signals can be highly increased, highly enhanced, because when electromagnetic radiation interacts with the metal nanoparticles, the free electron cloud of the nanoparticle can set in resonance with the electromagnetic field of the laser, and this provokes an enhancement of the electromagnetic field in the nearby of the surface of the nanoparticles. These local regions are called hotspot, and when a molecule is located into the hotspot, its Raman signals can be enhanced, increased in intensity. The reasons for this Raman enhancement are explained by two effects, one more physical effect, the electromagnetic enhancement, and one chemical effect, the chemical enhancement. The electromagnetic enhancement is a direct consequence of the roughness at the nanoscale of the metals, metal nanoparticles, because during normal Raman, the electromagnetic radiation interacts directly with the molecule, whereas during SERS analysis, the electromagnetic field is still modulated by the presence of metal nanoparticles, and the molecule experiences an enhanced electromagnetic field. And the intensity of the Raman signals are related to the square of the overall electromagnetic field incident to the on the molecule. The chemical enhancement instead occurs just when the molecule is chemisorbed onto the gold nanoparticle or metal nanoparticle in general, and a charge transfer effect can occur from the metal to the lower unoccupied molecular orbitals of the molecule, and vice versa. And this also brings an enhancement of Raman signals. Many nanosystems can be used in order to perform SERS analysis. We have prepared in our laboratories in last years different gold nanoparticles with a different shape and size, spheroidal or nanorods, but also more complicated systems such as core shell nanoparticles, for example, with a gold core and a silica shell that improves the chemical stability of these nanoparticles. But not only metal colloids can be used for SERS analysis, but also surfaces with a roughness at the nanoscale that can support hotspots in the same way. And surface-enhanced Raman scattering analysis can be designed in several ways. We have, for example, in-liquid assays, which are performed just mixing gold nanoparticle colloid with the analyte solution, and the laser is shined directly into the solution in order to perform Raman analysis. Or in dry condition analysis onto a SERS active surface, or the most innovative one, which is related to the use of a real sample, and we perform Raman analysis directly on a surface of this sample, which behaves itself as a surface active for surface-enhanced Raman scattering. Well, I want to show just a few examples about the different analytical strategies. This is a colorimetric assay and SERS assay based on in-liquid test that was optimized and studied here at the National Institute of Metrology a few years ago by Andrea Giovannozzi and Francesca Rolle that are here. This is related to the detection of melamine in a solution. Melamine is a nitrogen-rich molecule that was used in the past to false the protein content of milk, and it is very dangerous because it can provide kidney failure. And it was added, for example, to infant formula in China, and many children had problems with this. This colorimetric assay is based on the fact that melamine with these amino groups is able to set as a bridge between different gold nanoparticles and provoke their aggregation. The aggregation of gold nanoparticles can be monitored looking at the change in color of the colloid. And in this simple way, we are able to detect the analyte molecule just looking to the color change of the colloid. This is a very rapid assay, but in order to obtain more specific information about what molecule is into the solution, we can perform Raman analysis. And in this case, melamine is located as a bridge between nanoparticles, so it is actually into the hotspot, and we are able to detect in a very sensitive but also specific way the peak typical for the molecule. The other strategy to perform surface-enhanced Raman scattering technology was in dry condition analysis on surface on a solid surface, which is covered, for example, with gold nanoparticles that are attached to the surface in a quite homogeneous way, so that when we spot a drop of the analyte solution onto the surface, we are able to detect the typical Raman signals of the molecule in a very sensitive and selective way. More interesting application is this kind of substrate that were prepared here at the nano facility in INRiM. It is based on flexible silicon nanopillars covered with gold. In this case, when we spot a drop of analyte solution during evaporation of the solvent for a capillary effect, these nanopillars are able to provide a leaning process, and the gold head of these nanopillars get together, come closer, and hotspots are created to top tip sites. And again, in this case, the molecules, the analyte molecules, are trapped between the heads of these nanopillars. They are located into the hotspot, and we are able to detect their signals in a very sensitive way. I want to spend much more words about this quite innovative approach. In this case, we have contaminated surface at the bottom, and we drop on the contaminated surface gold nanoparticles on top as a smart dust, which is able to enhance the Raman signals. As you can see here, for example, we have a contaminated surface, so we have contamination spread homogeneously on the whole surface, and half of this surface is covered with gold nanoparticles. We have performed the Raman imaging analysis, so each pixel of this chemical image represents a Raman spectrum, and the color is related to the analyte Raman peaks. So in this case, in absence of gold nanoparticles, we can see very, very low intensity. We are about to 0 or very low intensity. We are not able to detect analyte in absence of gold nanoparticles, whereas in presence of gold nanoparticles, the signal intensity is extremely enhanced. So in this framework, I want to show a real case study, which is related to the detection of fungicide traces in situ directly on fruit peel. This case study was born from the necessity to develop a new rapid, portable, and versatile methods in order to protect organic cultures. We have selected for this study a probe molecule, which is pyrimethanil. This is a widely used pesticide for antibotrytis treatment, and this is a Raman active molecule with its typical Raman fingerprint. Okay, for this study we started from the comparison of 4 types of gold nanoparticles in order to select the best one for this application. We started from a deep characterization in order to obtain a well-defined nanomaterial which is able to give a standardized methodology. So we have evaluated the shape and size of 4 different batches of gold nanoparticles with different diameters using SEM, and we have also evaluated the size distribution. But the most important property for surface-enhanced Raman scattering analysis is actually the plasmon resonance wavelength. So we have performed UV visible spectroscopy to detect the plasmon resonance wavelength. And as you can see, as the diameter of gold nanoparticles increases, also the peak redshift, because this plasmon activity is a function of gold nanoparticle size. Secondly, we have evaluated the interaction between gold nanoparticles and the analyte. We have simply mixed them together, and we have monitored the colloid suspension for days. We have noticed that these are perfectly stable. The peak of the plasmon resonance does not shift, and this means that no chemical interaction between the analyte and gold nanoparticles is occurring in this case. This has 2 main consequences. First of all, in liquid medium analysis cannot be performed, and secondly, in this case, just the electromagnetic effect for Raman enhancement can be exploited. Well, then we have performed a test, self-efficiency test. We wanted to know what nanoparticles were working the best for this study, and we have selected gold nanoparticles with 120 nanometers diameter because they provided the best analytical enhancement factor, and this is probably for 2 reasons. The first one is that the plasmon peak of bigger nanoparticles better matches with the excitation laser wavelength we are using for this analysis, and the second one is that gold nanoparticles with a bigger diameter are able to arrange on the surface in a more proper way. So after having selected the best gold nanoparticles for this test, for this assay, we have demonstrated the possibility to detect pyrimethanil, our probe molecule, directly on the surface of a contaminated apple. So we have spotted gold nanoparticles directly on a fresh apple peel, and we have performed the Raman analysis directly in situ. As you can see here from this optical image, we have spread pyrimethanil using spray coating in order to simulate the real case application. This is a spot of pyrimethanil, and when we perform Raman imaging of this spot, we are not able to detect any signals of pyrimethanil. Again, the color scale bar is related to the intensity of a very specific Raman peak of this molecule. Whereas when we cover the spot with gold nanoparticles, in this case, Raman signals are hugely enhanced, and we are able to detect with high sensitivity and high specificity the contaminant, the pesticide, directly on fruit peel. So this is an interesting in situ approach directly on the sample. As far as we have demonstrated the possibility to qualitatively recognize the contaminant directly on the surface, we were curious about the possibility to have a quantitative calibration of this sample. We have performed analysis using increasingly contaminated surfaces, and after spectral normalization using reference peak related to gold nanoparticles in order to withdraw artifacts and undesired effects, we were able to find a linear correlation between Raman intensity and the concentration. This fit was performed using weighted total least square regression, and the linearity was quite satisfying, but unfortunately the uncertainty associated to the slope and to the intercept of this line were not negligible. So this might affect a lot quantification results, and the resolution of the method is not satisfying. For this reason, we have also performed multivariate regression method. Partial least square method was used in order to calibrate the methodology. In this case, the random variability of just one variable is overcome because the entire spectrum is considered in this case. And both calibration methods were validated using a validation test on several samples contaminated at the European low limit. The European legislation low limit for pyrimethanil on apples, and in both cases the calculated concentration, the obtained concentration, were compliant with the real concentration, but the partial least square method provided the best method stability. As a conclusion for this presentation, I want to stress the point that different gold nanoparticles with a different shape and size could provide a different enhancement effect. So a deep characterization of nanoparticles at the beginning of the methodology setup is needed in order to obtain very reproducible and stable results. Raman mapping strategy was used in this study in order to obtain reproducible results because it allows to overcome local dishomogeneities on the surface, and using this strategy it was possible to set up an analytical method in accordance with the European low limit. But the most potential of this method is its high versatility, because no specific chemical interaction between the molecule and gold nanoparticles is exploited in this case. But in principle, any molecule could behave in the same way. Okay, I want to thank my research group, my supervisors, and you for the attention.
Thank you for your presentation. Are there any questions?
I have just a curiosity about the samples. You used your technique on apples, solid, in terms of material structures. And can you use the Raman spectroscopy technique with water sample, no water, liquid sample, or something like that?
Yes, sure. Raman spectroscopy is a versatile technique that can be used for solid surfaces in order to detect contaminants on the top, but also it is mainly used for crystals in order to study vibrations into the solid samples. And actually, this technique was born for inorganic analysis. It is just moving now towards organic and food analysis, but also for liquids and also for gas samples can be used, because it exploits the fact that when the laser interacts with the matter, the light is inelastically scattered, whether if solid, liquid, or gas phase.
Okay. Thank you.
Okay. Other questions?
This is just one of my curiosity. Are you going to try with other molecules in the future?
Yes, I hope yes, because actually this pesticide was just a probe molecule. It is not particularly harmful to humans. It is harmful, for example, for aquatic environment, and it was selected mainly because it does not interact directly with the gold nanoparticles, but it is of interest to give a wide application of this method using also other pesticides or other food contaminants. And the same strategy can also be used for biomedical applications in general, for example, on biomedical materials and so on.
And I have another question. Sure. If you suppose that you can use this method in situ, as for example, I see the fruit there, do you think you will find sampling problems?
Yes, sampling problems during food analysis are always problems, mainly because the huge amount of sample that sometimes have to be tested in a very rapid way. For example, at the arbor when big amounts of sample have to be accepted or rejected in very few times. So sampling in food analysis is a very crucial point. Sure, reproducibility and repeatability of this method have to be driven to a metrological level in order to be able to introduce these techniques in food quality and food safety procedures at the European level.
So I have a curiosity. So in the beginning of the presentation, you said that part of the signal amplification could be due to charge transfer associated with molecular chemisorption. I would expect that this charge transfer might not only amplify the signal, but actually change the Raman signal because it changes the structural properties of the molecule. Can you comment on that?
Yes, sure. This is a good point. Actually, when we are in presence of CERS signals, we expect also a Raman shift of the bands, and also sometimes Raman bands after enhancement are broadened, and also some modes that were not available for normal Raman become available during CERS. So it is also very difficult to give an interpretation to Raman spectra for this reason in case of enhancement effect.
Last question.
I was wondering, do you need to know which kind of contaminant are you looking for in order to get it?
In this very first study, we perfectly knew what was the molecule, but the potential of the technique is that it is a fingerprint technology. So in principle, looking at the Raman fingerprint, the pattern of signals which are specific for the molecule, you are able to recognize what molecule is on the top of the surface. Actually, when you have a mix of molecules, probably the pattern will be very complex because it will be the sum of all these signals, and it will be difficult to recognize what kind of molecules are on the surface. But if you have, for example, target signals which are very specific for your molecule, you are able to detect them in a very specific way.
Okay, thank you again, Lisa.
Okay, thank you.
The next speaker is Riccardo Aragona from Ghent University. ICRF, traveling wave antennas for fusion devices.
Oh, can you hear me? Yeah? Oh, it's good. Okay. So, good morning. Today I will try to driving you a little bit of curiosity on what I'm doing at the LPP laboratory, that is Laboratory for Plasma Physics, that is in Brussels, Belgium, although I'm a student from Ghent University, also in Belgium. So first things is a brief overview, just to give you some ideas about the whole environment in which I'm working on, that is ion cyclotron radio frequency, and we'll explain later what this does means. And there will be a specific antenna, the traveling wave antenna, for heating of thermonuclear fusion devices. We have seen from the previous presentation, we start talking about plasmas. Also here we will talk about plasma, but for energy production. Why? Because we want to exploit fusion for energy production. Why fusion? Because fusion has a large specific energy compared to the available source of energy that we have now on Earth. Just to give you an idea, with 1 liter of seawater plus 5 grams of lithium, we have the equivalent of 360 liters of petrol. And then later on I will go more on deep on this ion cyclotron heating. You can already infer from ions, so we want to go directly through the ions, and I remember to you that plasma is ionized gas. So let's go a little bit more deep in fusion. You know very well this diagram, the binding energy diagram, and you can see that the binding energy diagram, that is the diagram that gives you the average binding energy per nucleon versus the number of nucleons, could be divided in 2 areas. The right areas is the area of fission, and the left area is the area of fusion. We want to stay in this area here, and you see what is mainly fusion. You already know that. It's just taking some very light nuclei, let them collide together, and the output is just energy. And you see as an example, we take deuterium, one of the isotopes of hydrogen with tritium, that is here, and we get out 17.5 MeV of energy. So here is depicted the reaction. But why, as an example, DT and not one of the other reaction as an example, this one that has higher energy output? Because if you want to maximize the power output, you will see from this formula, we have to maximize the reactivity of the fuel. And here is depicted as a function of the temperature, the reactivity, and you see that for the DT reaction, we have a peak at lower temperature. Why? And you see already that this temperature, although they are expressing kilo electron volt, are quite high, and so DT seems to be the best option. So again, we are talking about plasmas. You know, plasma is ionized gas. Just to have an idea what are the temperature that we need for ionized gas to become useful for energy production, we have the solar core temperature. And so you know solar is the best and biggest nuclear fusion reactor that we have here, at least nearby the Earth. And the temperature inside the solar core is just 800, and not just, but is 860 electron volt, that is roughly 10 million Kelvin. But here, to have on Earth fusion reaction, we need to go for a higher temperature. So in the order of 15K electron volt, that is roughly 174 million degree. Okay, so how can we confine a matter that has this temperature, knowing that melting temperature of metal is so low? Okay, we go via magnetic confinement. So you know that if we have a constant magnetic field, and if we inject a particle inside a constant magnetic field, this particle will experience a trajectory that is helical if it has a component along the B field. If not, it's simply moving around in a circle. And the frequency of this circle, the motion of this circle, is described by the cyclotron frequency, and the radii are described by the Larmor radius. And I just want to remind you that particles, okay, they can spiral inside magnetic field lines, but under the effect of external forces, and here I just want to point to you to 2 possible external forces, they will also experience a drift. As an example, if we put an electric field in this kind of environment, both particles will experience a drift in the same direction. While if you have a gradient of the magnetic field, the particle will experience a drift that tends to separate particles. Why this is important? Because now we want to exploit magnetic confinement, so confining plasma particles with magnets. So, here. One example is exploiting the fact that we have an adiabatic invariant. It's just if we put a gradient of magnetic fields, we can trap particles. And this is a well-known configuration. This is called magnetic mirror. Magnetic mirror in the sense that particles just bounce inside these structures. But all particles can stay inside this particle? Of course not, or unfortunately not. Exists in the velocity space a cone that is called the loss cone, in which particles that stay here in this diagram will just flew out of this magnetic mirror. So one solution could be, okay, I can close these magnetic surfaces, creating a donut shape. And this is the tokamak concept. One of the possible concepts of closing magnetic line is the tokamak concept. And we have, again, a magnetic field lines created by these toroidal field coils. But unfortunately, this is still not enough, because you see that due to the toroidal geometry, we have a major density of flux lines in the inner part of the torus in respect to the outer part, and this gives rise to charge separation for one of the effects that we have said before. And the charge separation built up an electric field, and this electric field gives due to the E cross B drift that pushes the plasma out. The solution is to add a poloidal magnetic field component that bends the line. These are the line in which particles just go all around with the helical trajectories, and also this trajectories becomes helicals, moving from the outside to the inside and then again. And this, as an average effect, will cancel out this drift. But these surfaces here, we can describe these surfaces dividing in two domains. One is the completely closed flux surfaces, and the other domain is the one outside the flux surface. And I just remind to you this definition, scrape of layer, that is the region outside the last flux closed surface. And this will be important for the upcoming discussion. So we have seen that we are driving here a current, so it means the ionized gas is a good conductor. Yes, it's a good conductor. It is described by a resistivity. So first things we need to, and we want to heat up plasma. Okay, so we can drive a current again inside, and via the ohmic transformer action, we can heat up this plasma. But unfortunately, the resistivity goes as the temperature as power -3 to over half, and it can be computed that the temperature that we can achieve with ohmic heating is not enough for the nuclear fusion reactor. So what we need, actually, is to use other auxiliary heating technique, and one of these is the neutral beam injection. Let's see if there is something. Okay, it's not working, sorry. There was an... okay, so here you have to see here like a cannon that is injecting neutral particles. Neutral particles are entering inside this confinement area. They will be ionized, so they become charged. So they will start following the magnetic field lines, and then via Coulomb collisions or other kind of collisions, they will damp their momentum on the background plasma, and this will give rise to a heating effect. The other one is the one that we are interested in, is to exploit radio frequency effects, resonance effect on the plasma particles. And the intuitive idea is that if we inject radio frequency waves at the proper cyclotron frequency, then we can have transfer of energy from the wave to the particles. Here what is important is that this message here is to tell you that it's possible to solve the Maxwell's equation, and especially the wave equation, inside a magnetized plasma, and to actually see how the fields behave. This is a picture of inside of a tokamak machine, and this is a computation of the fields. This is an antenna radiated by this antenna inside this machine. Not only is it important to know the fields, but also it's important to know where power is damped. And here we see a computation for the ether device. This is the antenna, and you see that in this case the antenna and the scenario are very good, in the sense that the maximum of power absorption for the plasma is exactly in the core, so exactly in the point where we want to have the higher temperature. What is important is to say that with this kind of analysis it's possible to know what is the most suitable plasma modes that we need to excite to obtain this good deposition of power. And let's call this as K optimal. So now we see a little bit more how it looks like an ion cyclotron system. This is what you will see from the inside of the machine. So this part here are the antennas. But the rest of the system outside the machine could be a little bit complicated, but mainly this is the principal schematics, is made by a generator that actually creates and produces the RF power that you want to put inside the plasma. Here is the plasma. And then there is a transmission line that moves the power from the generator to the antenna. And then unfortunately we also need a matching unit that match the impedance of the generator to the impedance seen from the antenna. This because we want to have the maximum throughout of the power from the generator to the antenna. On this side is a real example of these simple schematics in the access upgrade machine in Germany. And you see that is a little bit more complicated. But basically, if we look at the antenna, that is the main work that I'm doing now, and how an antenna could work in such kind of an environment, it's a little bit more different than normal antennas. So it's just simple pieces of metal in which we would like to drive a current, and suppose this is connected to the metal background plate here, and here you have to imagine to have a sort of coaxials that's come, and the inner part of the coaxial will just start driving current on this metal strap. And once you have a current, you have a magnetic field. And once you have a magnetic field, of course, this is a cross cut here of the plasma like this one, just to tell you that the plasma is not homogeneous. You will have an electric and magnetic field that propagates from the antenna through inside the plasma. Important thing here is to note that in this vacuum layer, unfortunately, fields are not propagative, but are only evanescent. And so the point is that to have enough power become propagative, enough voltage, if you want, or enough electric field here for a wave to become propagative, we need to have a huge field here at the antenna side. And this technologically is quite a problem. So we have seen before that I told you about an optimum in the spectrum for the plasma modes. So we start from knowing this optimum from the previous computation, but this optimum is just one of a more general case spectrum. And now we want to build a current distribution that has something to do with this spectrum. And this current distribution is connected to an antenna excitation function. That is the antenna excitation function that we put inside the pointing theorem vector, or if you want, we compute in order to compute how much power actually reached the plasma. The other important part is the plasma response. So how the plasma responds to the fields that we put in front of this. And this gives us the possibility to compute this coupling. And we see later how to have this current distribution. So we have a series of straps. On each of these straps we have a current. Current has a maximum amplitude and then a phase difference. If this is the case, we can compute the Fourier transform of this, and we have a KZ spectrum, where K is the wave vector. Here we are only interested in the Z components, supposing that the Z axis is the axis parallel to the background magnetic field. And we could call this KZ, or K parallel is exactly the same. So from the point of view of the coupling, we said that plasma behaves differently depending on his composition and his how it is made in some sense. And this can be computed as a surface conductance, that is the inverse of a surface impedance, and just take the real part, because here this is the real part of the pointing vector or flux. That is what we are interested in. And what is the effect? If we take a cut here in the KY, we see that the blue lines are the antenna spectrum components, and the plasma actually is shaping the antenna spectrum components. And what is important here in this information is that you see that power, this gives you an indication of how much power that is inside the spectrum actually goes inside the plasma. And you see that for very low KZ, we have much more contribution. The point is, okay, we can optimize this, yes, of course. But what are the knobs? One of the knobs is the interdistance between the antenna straps, and you see here depicted the effect. You see the larger you go, the worse it is, and the shorter you come nearby, and the best it is. Why? Because you are pushing out the secondary peaks. The other one is, of course, increasing the number of straps. And increasing the number of straps, not surprisingly, increase the power, because the power scales directly as the number of straps. Suppose that you have a current amplitude on the strap. So now we have seen more or less how to have this current distribution, why it is important to have this current distribution, and now see how to implement this. There are two possibilities. One is we have a series of straps. We can feed all the straps individually, or we can rely on traveling wave antennas. That is a good interesting things, and how behave a traveling wave antenna. So you have an object here. You have here all your metal bars or metal strap. you put the capacitors on top of that, you tune this system, becomes a resonance system, and then via the mutual coupling of all this, what you have is that if you inject a signal or power here in this input port, you will see an input power outside. So you have actually a traveling wave that moves inside the structures, and this traveling wave gives you the right current distribution that you want to have in order to heat the plasma inside. Then we can do something more interesting and computing actually the fields that you see are leaking from the structures. So here, this is the evanescence layer. So you have evanescence fields. If you remove the plasma, these fields just die out radially, going through this direction. That is the radial direction going through the core. But if you add a plasma inside, you see that these evanescence fields at some point trigger some plasma modes. So we are actually putting power inside these modes of the plasma that goes radially inside. Okay, but how really to make this? We can put these traveling wave structures inside a resonant ring, and it is called resonant ring because it's possible to put proper length of these structures in order that this in orange is the path of the power, that the powers just start moving all around in a resonant way. And you see there are points in which this red line is the maximum, is the power put in from the generator. All the power is going exactly here in these structures, and then following the green line is just radiated inside the plasma. The main point is that, okay, this thing is good, but if we move the plasma, what happened? Because plasma, of course, is not staying there, but just moving all around. Okay, and you see that the effect of the plasma in a certain area here of this power versus the loading resistance is quite flat. And this gives us a good feedback on the system. But now we can compare an oldie, let's say a normal used design as the one you have seen before with our new design, and you can see that from here, you can see that there is a huge advantage. And at for some components of the spectrum, we have almost a factor of 3 of improvement. This is what we are trying to see a possible implementation on a nowadays machine to test our new antennas. These are again computation of the fields inside the plasma. But looking forward, because this is the main topic, is just to try to put this kind of antennas inside a real fusion reactor. And this is because in the future will be needed to put a lot of input power to get a lot more output power from the plasma. And the amount of power that it is needed, as an example for a demo reactor, will be in the order of 70 megawatts to have something around 1 gigawatt thermal energy output. From the point of view of the antenna, what we are trying to do is to put each section independent, but now we are also working on a more interesting idea that is to go all around the structures. This will give you an enhanced effect from the point of view of we want to put the power in that mode, and with a very long antenna, you know that if you have a lot of strap you have seen, you will have almost a beam. So you are able to choose where to put the power. And then that's it. So I think that summarizing, more or less, I have given you some ideas, and you can agree with me that with this new design we can possibly put a much more power inside the plasma, so we will experience a large increase in the coupling. Then the system is load resilient in the sense that if the plasma just moving from the structures will not be affected too much. And then we will have for sure an highly selective spectrum, and this will be not only good from the technical point of view, but especially from the physical point of view. And so I will thank you very much for your attention.
Okay, thank you. Any questions?
In the last line, you repeat that you have to choose an optimal value for key, and in some slide before you told us that the value of key,
optimal key,
the optimal key depends on 2 parameters. That's the next one. Next one.
Previous next one.
Next one, I think.
This one.
No. Well, the function, you said it depends on two parameters in order to find the optimal value for key. That one, I guess. And my question is, how do you find the optimization? I mean, do you use Lagrangian multiplier for the two parameters that are dependent?
No. It's much more simple in the sense that the difficult part is to analyze plasma. In the sense that I try to give you some ideas from here, and the point is that when you compute how waves propagates inside the plasma, you know that plasma can sustain some MHD modes. So you know that some MHD modes are better than others from the point of view of putting power where you want. So here the optimization is just looking inside the possible, or it's really brute force, because solving this problem is already very difficult. Because here is not just a cold plasma approximation, very easy to be solved also analytically. This is the most realistic plasma description that you can have. You need to have a kinetic description because you want to put high energetic particles inside. So the only way to solve this problem is just numerically. And once you have a numerical solution of this, you just plot the curve and say, ooh, the peak is there, so I want to go there. From the antenna point of view, is more simple. The effect of the plasma is computed. The one that I show you is just a simplified model that is a slab model. So the plasma is just slabs. There's no curvature, nothing. And this is just, again, solving Maxwell's equations, and in particular in the magnetized plasma case. And you will have, yes, of course, the wave vector is function of 3 components, but one is fixed by the relation, and you have just 2 free to move. And then you see from here that there are points where you have here very low value, and this will cut out this. So it's just, you look at the spectrum, you know that if you go for low K, it's better, and then you try to think how to make an antenna to just stay there. Seems simple, but it's not. It's just really brute force.
Other questions? The last one.
I was curious, would this technology also have application in principle to stellarator-like machines, or is it just for tokamak machines?
This one is mainly for tokamak machine because the point is that stellarators, how they are made, they don't want to have current driven. And from here, it's a little bit difficult, but can be shown that this you see this spectrum has a large parallel component. That means that you are actually driving a little bit of current inside the plasma. And this is not good for the stellarator because stellarator relies on the fact that if you have static magnetic field, the static magnetic field that you create with the stellarator is enough for confine the plasma. On contrary, tokamak needs to drive currents inside. And this is another, but this is another good point because with this system you can drive also current in a tokamak and so help the tokamak to have this sort of enhanced confinement, or not confinement, but control of stability is better. But in our lab we have developed an antenna for a stellarator, for the Vanderstein 7X stellarator in Germany, and this antenna will be used to study the confinement property because our system just going exactly at the ions is able to create very high energetic tail in the temperature distribution, and this will be used as a tool to study if the stellarator configuration is better than the tokamak configuration.
Okay. Thanks. Thank you again for your presentation. The last speaker of this session is Paolo Brogi, a digital avalanche pixel sensor for charged particle detection.
Good morning, everybody. I am Paolo, and we will talk you to a new avalanche pixel sensor for charged particle detection. A brief outline of my presentation. I will do a brief introduction, in particular to the concept and the architecture of the sensor, a preliminary characterization of the parameter of the sensor. Then I will show you the beam test layout of this, of the first demonstrator of this sensor, and finally the summary and perspectives. The concept behind this sensor is quite simple. we have we use the idea is to use two avalanche detector, Geiger mode avalanche detector called SPAD. Is a single photon avalanche detector that are quite similar to CPM, for who of you know CPM, silicon photomultiplier. And the idea is to put in coincidence two of these detectors in a front-to-front configuration to detect charged particles instead of photons. The advantage of this detector is that we have a digital readout, time in performance, low power consumption, low material budget, and a reduced dark count rate respect to standard CPM. A brief insight in the active area structure. These are the SPADs. We have choose two different types of SPAD for this demonstrator. The type 1 SPAD that use a pi plus NOL junction to do the multiplication of the charge and so the discharge. And the other one, the type 2 with a PUL and ISO junction where the multiplication occurs. Both these sensors are built in a standard 150 nanometers CMOS process. This is mandatory to build also the electronics in the same pixel where the active detector is placed. In this slide you see a cross-section of a pixel of the detector in which you can see the SPAD active detector and the electronics that you can see the electronic that is inside the pixel structure of the detector. The two layers are vertically integrated via bump bonding procedure, and the two detectors have a metallized shield to avoid optical crosstalk between each others. And the dimension of a pixel is 50 by 75 micron. Okay, a brief introduction to the electronics. In this slide you have electrical diagram of the pixel structure. You can see that of course the detector is represented like a diode polarized with this high voltage bias that is in order of 20 volt. And there is a quenching transistor to stop the discharge in the detector. And an enable register we use to individually enable or disable each pixel through, and the enable register acts in two ways. One is disabling this M2 recharge transistor, and the other is as one of the input of this AND gate to disable the output of the detector itself. You can see here a clamping transistor to 1.8 volt. This is put here to reduce the pulse rate of the detector in order to use 1.8 volt transistor in the electronic part for the front-end readout, because are more compact, faster, and also low power consumption than the 3.3 volt transistor used for the detector part itself. Okay. The other thing we have, the other electronics we implement in the pixel is a monostable for programmable monostable for the pulse shortening. This is simple why we use the monostable, because in this way we can shrink the output pulses of the detector, avoiding much more spurious accidental coincidence that could contribute to dark count signal. Like in principle does not affect the real detection of charged particle because the signal are in coincidence. And then you can see the AND gate, the output AND gate. This collect the two input signal from the two vertically integrated detector, And okay, the programmable monostable have difference with pulse width from 0.75 to 100.510 nanoseconds. And you can see the last part of the electrical diagram. That is the part you use to read out the signal of the detector. In particular, the signal coming from the output coincidence goes to 1-bit memory that is simply a latch-up flip-flop to store the data acquired by the pixel, and that is connected to a second flip-flop used as output register. This is connected through a multiplexer that allows to connect or the output register to the bit memory, so we can register in the output register the value of the data of the pixel, or if we switch the multiplexer, we connect this output register to the previous output register of the previous pixel in the same row. In this way, we can virtually acquire while the detector is taking data, so we have no dead time during to do it to the acquisition. I show you a layout of the two chips that form the final assembly. The chip 1 is called also father chips, and the chip 2 is called also son chip. You can see the bump bonding area and also the wire bonding area in the two chips. Also, chip 2 have wire bonding in this design to allow to test separately the two chip, and in the final configuration after vertical integration, this is the final layout. You can communicate, you can bond the final assembly through the paths in the father chip to the package. Going a bit in detail in the pixel array, we have for this demonstrator an array composed by 16 rows of 48 spots each. The pixel size, as I have already said, is 50 by 75 micron, but we have have a 50 by 50 micron area is dedicated to the detector, and there other 25 by 50 areas dedicated to the electronic and the bonding pads. Then, okay, we have a different segmentation inside the same row of the array, because we want to also to exploit different active area size to see how the detector behave. So we have different area for the active part that goes from 30 by 30 micron to 45 by 45 micron. This is a micrograph of the chip itself. Okay, it's a bit misleading, but the row are along the horizontal view. But you can see that we have also a part without the metallization of the spots to permit to test with light the two chips. Okay, going to the characterization of the detector, we have measured the single photon timing resolution with on a 10 micron device with a blue laser with a 70 picosecond full width at maximum, and the time resolution results of 60 picosecond for the type 1 avalanche detector and 170 picosecond for the type 2 detector. The other things we have measured is the breakdown voltage for 5 different chips of the same type. We measured the breakdown voltage for type 1 and type 2 detectors, and we have a good uniformity inside the same chip for the breakdown voltage, less than 20 millivolt, and but for type 1 we have a large difference between one chip and another in breakdown voltage also, if this is not a great issue, but okay, there is. And the other thing we have measured is the dark count rate. Dark count rate for different size of the active area, and for both type of the of device. And we found a median dark count rate of 2.2 kilohertz for the largest size of active part, and this is let's say it's expected for this type of detector, also for is in this order also for more optimized CPM detector. Finally, we look at the dark count rate of the final assembly, so the coincidence between the two chips. In this plot, you can see the dark count rate of the two SIP without the coincidence, and the dark count rate of the final assembly with the coincidence of different length of the pulse. You can see that there is a great reduction of the dark count rate, about 4 order of magnitude, and you have a final dark count rate of about tens of counts per seconds 4 millimeters square. And this is what we expect. Finally, we have tested this prototype on test beam. In particular, on September of this year, we have tested it at CERN SPS North Area facility. We have tested 2 prototypes of IPIX with an auxiliary detector, a beam tracker, and we have positrons and hadrons beams of different energy from 50 to 300 GeV, and we reached to collect a great amount of data. This is a layout of the readout and control chain of the test beam setup. You can see the APIX support card, where APIX is plugged in this ZIF connector and is wired on this chip carrier. And this support card have a flat cable with LVDS signals to control and acquire data, and another connector that permits to control to supply the bias voltages from outside the board and through programmable voltage sources quickly. Okay. This is we have a dedicated control and acquisition board that uses an FPGA to talk with the PC through optical fibers, and also the voltage sources are programmable through LAN, so we can change the bias of the detector without entering in the experimental hall. This is the layout of the experimental apparatus. We have 7 XY layers of silicon strip, and around the middle we have placed the 2 APIX assembly. The layers of strips are different. We have 5 layers with a coarse segmentation of about 700 micron, and 2 more fine segmented strips layers with a segmentation of about 80 micron. Then the trigger is provided by the coincidence of 2 scintillators, and we have also a random OSPIL trigger to measure the APIX dark count rate and also the strip pedestal. Moreover, APIX is provided with an asynchronous reset at 1 MHz to allow to reduce the integration of dark count rate in in the chip. So this is just to show you that APIX see charged particle. That is not obvious, okay, because it's the first type of detector of this type taken to a test beam, is nothing particular because analysis on September, mid of September data is still ongoing. We hope to measure and confident to measure the efficiency of this detector, hopefully also independence of the bias voltage. And this is only a heat map of the two layers of APIX. A heat map, and the coordinates are column and row number. You can see we have a blank part that is where we have disabled the pixel because in this part there are the not shielded pixels that are very noisy, and also we have disabled some anomalous noisy pixel. And this is simple an heat map where you can see the type 2 and type 1 detector technology at different bias voltage. And to show you that is not only dark count, this is the map of the dark count. This is the heat map taken with the random trigger, and also if of course this is these plots have about 3 times less statistics than the previous. This is cannot be only dark count, but are charged particle. Finally, a summary. The strengths of this detector are the fine segmentation. We can reach easily tens of micron. The complete digital readout. The low material budget because the active area is around the micron size. So we can tune the sensor to few microns without particular problem. The timing resolution that can be also improved than the one I've shown you, but also have timing resolution capabilities. And the most of all, the low power consumption and low power bias voltage of this device. The weaknesses could be the radiation tolerance. This is an open question because we have to investigate the radiation tolerance. The geometrical efficiency, because we have an electronic inside the pixel, so it's reduced. And the cost and accessibility of this vertical integration process, because for the moment is really demanding. And the current status and future plans for this project is, current status, we have a fully operative prototype that we have made a bin test of this prototype, hopeful successfully. We are analyzing data of this bin test. We hope to have as soon the efficiency of this detector. We are planning a radiation hardness test, and we are studying the design of a new prototype with a larger array, an improved fill factor, and an optimized timing, and also an optimizer power consumption. Thanks.
Your presentation. Are there any questions? I think we have time for just for one question.
Thank you for the presentation. Can you specify for what real application you would like to use this detector? Means for monitor the beam or like for tracking system?
We opt for tracking system because the really advantage is this low digital readout of course and low power consumption. We are with this demonstrator that is not optimized. We have a power consumption less than 15 millivolt. Yeah. But this is can be optimized a lot because we use a comparator that have a reference voltage that you can tune.
This is not the main question for the tracking system. You should cover a huge space, and you also should be, let's say, time stability.
Okay, power consumption is
will not allow you to do that.
Sorry?
This detector will, let's say, not allow you to do that long-term stability work, because, for example, now in CERN developed like a jam detector. Why you didn't compare jam detector with your device?
But it has a good resolution because we have a very fine segmentation, tens of micron. It's fully digital,
it
no
will
gas.
Immediately die after one day of work, I believe.
I don't know. We have to test. Probably yes, but we don't know. Of course, it's not probably for LXC high luminosity, but for other application of particle tracking could be enough. Of course, I have not thinking to install it probably on LXC because okay, the luminosity is really high, but okay, there is not only LSC. I hope so for lower luminosity. We hope, because we have not probably bulk damage, but okay, we don't know.
Okay, thank you again, Paolo. Now there is the coffee break, but unfortunately we have just 5 minutes for the coffee break.
Sì, Sure. Sì, sì, sì.
Allora, dove le tenete le presentazioni?
Allora.
Quindi questa la chiudiamo perché è finita. Poche le slide. Vabbè, 17.
20 minuti più 5 per le domande che speriamo di tenere al...
Io sento il fatto la prova.
Okay, we have to start, even if we are not complete. But so we start this session of particle physics. We need the full screen. I think it's this one. Okay. So welcome back, and we start this session with this talk held by Irene Nutini about the physics of neutrinos and other very interesting things that I studied in the first degree of the physics, and then I left for other stuff, and I'm very interested now. So we can go on, and please, we have to be quite. We are strict with the time, so I will use this atomic clock to measure with exceedingly good accuracy 20 minutes. Okay, and then if we have some question, we can start.
No? Ah, quest'altro. Okay. So, hi everybody, I'm Irene Nutini from Gran Sasso Science Institute, and I'm here to present the first pion on argon total cross-section measurement that was made with the Lariat experiment. So, the Lariat experiment is part of the neutrino physics, accelerator neutrino physics program at Fermilab. Our primary goals are studying neutrino flavor oscillations and the existence of, investigating the existence of sterile neutrinos. So, what this kind of experiments are meant to do, they are firing beam of neutrinos into the detector. The neutrinos will interact, and the secondary charged particles that are produced will be detected, and their information, so the leptons, mesons, and other nucleons, and their detected information will be recorded and utilized to recover the information about the neutrino. So the liquid argon time projection chamber technology, that is the technology that we are using in our experiment, is an excellent choice for this kind of neutrino detectors. We use liquid argon because it's very dense, it's denser than water, and it's relatively abundant in the atmosphere, so we can extract it and purify it quite easily. And it has a high electron lifetime, so the ionization electrons can move through the medium without being absorbed. And also it has a nice scintillation light yield, and the photons are, and it's transparent to the scintillation photons. So here there is a sketch of the liquid argon time projection chamber principle of operation. So you have a neutrino that interacts on an argon nucleus. Secondary charged particles are produced. They cross the medium. They ionize it. So the ionization electrons drift to these anode wire planes due to this electric field. They are collected to on these planes, and the charge and of the secondary particle is therefore collected. At the same time, the scintillation light that is produced by the charged particles while it crosses the medium is collected by optical devices like the PMTs. So here there is another sketch on how the LAR-TPC works. So we have two anode wire planes that can make you have a 2D reconstruction of your events. And then you have also the information about the drift time that I was saying when the electron starts to move from the ionization track to the anode wire planes. And if you collect all the three information together, you can get to a 3D reconstruction of your event. So the very nice thing of this kind of technology is that you can have a 3D imaging with a millimeter space resolution that is related to the wire pitch of your anode planes. You can also have calorimetry information because you actually see the charge that is collected on the wires, and also you can get also to particle identification capabilities. So let's have a look, a very quick look at the liquid argon neutrino experiments in the United States. we have their main goal is to have a very large active mass because they have to compensate for the small neutrino interaction cross-section, and they wanted to identify the different kind of neutrino flavor and measure their for momentum to study, as I said before, oscillation parameters and in sterile neutrino studies. So there is the long baseline neutrino program with the Dune project that is meant mostly to study the CP violation parameters and the oscillation parameters in general, while there is the short baseline neutrino program that will be held at Fermilab actually, and we have the 3 TPC experiments, Microboon, Icarus, and SBND, that are meant mostly to study the existence of light sterile neutrinos. So after this brief introduction on TPCs, let's move to my experiment. So why Lariat? Lariat stands for liquid argon TPC in a test beam. And the TPC in a test beam facility is actually well suited to study all the charged particles that are produced in the energy range that is relevant to these short and long baseline neutrino programs that I was talking about before. So for example, here we see the spectrum of the secondary charged particles that are produced in a neutrino interaction. This is a Dune simulation, and here we see these 2 bands that corresponds to the Lariat tertiary beam in low energy and high energy tone. So we can produce a tertiary beam which is composed to the same particles with similar energies of the particles that are actually produced in a neutrino interaction. So let's have a quick look at the sizes. Okay, here we see the big one, and this is just 1/4 of the Dune experiment. So this is the 10 kiloton, one of the 10 kiloton LAR-TPC module of Dune. This one inside is the Microboon TPC, which is 80 tons, and the small dot actually here, it's the Lariat TPC. We are 1/4 of ton liquid argon active mass, but as we like to say, we are a small detector with big art, and we can also do great physics, I guess. So, which is our mission, is to execute a comprehensive program designed to study and characterize the TPC performance in the energy range that is relevant, as I said, to these forthcoming neutrino experiments. Our physics goals are mainly to study the hadron-on-argon interactions, and what I'm going to present is the pion-on-argon total cross-section measurement. We want also to study the electron gamma shower identification in the TPCs that will be important to identify different flavor neutrino interactions and secondary products in the TPCs, and also particle sign determination in the absence of a magnetic field using the topology in the TPC. And this is quite a challenging idea because usually you need the magnetic field to define which is the charge of your particle. And also we want to provide a Gen 4 validation because there are not yet models that are tuned on argon. We have also R&D goals. That the main one is the improvement of the energy resolution of our detector through the combination of the scintillation light and ionization charge signal. And in general, we want to study the TPC event reconstruction and calorimetry systematics. So let's have a closer look at the experiment. So this is the Lariat cryostat that is hosted in the Fermilab test beam facility. We started taking data last year in May 2015. Our first run lasted 3 months. The second run, it has been this year, from February to July, and we have another run 3, that is planned for the next year. So here we see Lariat in the Fermilab test beam facility. So this is the Fermilab area. Fermilab area, the main injector, Fermilab Wilson Hall, and here this is the Linux line that goes to the Fermilab test beam facility. So let's take a closer look again, and here is the Lariat beamline. So we have the primary protons, high energy protons, that are shot on an aluminum target. Therefore, a secondary pion of beam composed of pions is produced with an energy around from 8 to 80 GeV. It's tunable, actually. And this is shot on a copper target. And here we go to our tertiary beam. This tertiary beam is composed by different charged particles, mainly are pions. And utilizing our dipole magnets, we can select different momentum range from 200 to 1500 MeV. We have also several auxiliary detectors along the beam line, and we use them to monitor the beam that is impinging on the TPC. So here there is an example on how we can use our beamline detectors to have an information before the particles get to the TPC. We have four multi-wire proportional chambers and the two bending magnets, and they allow us to reconstruct the particle momentum before it gets to the TPC. We also have two time-of-flight detectors at the start and at the end of the beamline, and utilizing the time of flight in conjunction with the momentum, we can get to this scatter plot that can make us discriminate among several particle species. So, for example, here it is the data, Lariat data from a positive run, and we can see just having time of flight, reconstructed time of flight and reconstructed momentum, you can see different population of your tertiary beam. You see the pion, muon, electron population, kaon population, proton population, and a small deuteron population. So this is quite interesting because you actually have a particle identification before the unknown particle enters the TPC. So let's then move to the cryostat, and inside it we have our TPC that is hosted inside the cryostat with the cathode plane, the anode wire planes, and that are read out with the pulse shaping and amplified code electronics. We have also this light collection system port that is facing the anode wires. You might see the grid here of the anode wires. And our light collection system is composed of two cryogenic PMTs and also three SiPMs on custom pre-amplified readout board. So we have different light collection devices that we want to test to see which one could be better to actually collect the liquid argon scintillation light. So the thing is that liquid argon scintillation light has a wavelength of 128 nanometers, so it's in the very ultraviolet, while the optical devices that we are using are sensitive to optical photons. So we need to shift the liquid argon scintillation light, and we use this wavelength shifting TPB reflector foils that are covering all the TPC walls to shift the scintillation light into the visible spectrum. So here we see these white foils that are covering all the walls, and they ensure us a more uniform and higher light yield with respect to the traditional technology. So instead, if we move inside to see the TPC itself, it's actually, as I said, a small TPC, 90 centimeter thickness along the beam axis, 47 centimeters width, that is the drift length, the maximum drift length, and 40 centimeters height. It is read out with custom code electronics that ensure us a very good signal-to-noise ratio compared to that is around 50, 70 to 1. That is a great improvement compared to other similar size neutrino experiments using worm electronics that usually got to 15, 20 to 1 signal-to-noise ratio. So let's move then, after this brief introduction on TPCs in general, let's move to the main topic of the talk, and that be the pion on argon cross-section measurement that has been actually the first measurement that has been made by our experiment, and it puts together all the various aspects of our experiment itself. So why we were so interested in the pion on argon interaction this is because pions are produced in a noticeable number in GeV neutrino interactions with argon nuclei, and observing the pion on argon interaction, we can study reconstruction systematics and calorimetry in TPCs in general, and also we can tune other nucleus interaction and nuclear structure models in Monte Carlo generators such as GENT4 and neutrino generators like Gini. So the pion on argon cross-section, the total and also the exclusive channel will play an important role in constraints the systematics of the neutrino oscillation measurements. Moreover, the cool thing is that there haven't been no measurement of the total pion on argon cross-section until ours, and the predictions are only for few energies and come from interpolation between lighter and heavier nuclei. So here we see a plot, for example, in which you can get to an interpolation for pi plus at this kind of energy. So what we want to provide is the cross-section measurement in a wide range of energies. So that is the challenging idea. So here there are Lariat's data, Lariat's event displays. Okay, I will try to be faster. So here we see different interaction topologies for strong interaction. And these are quite cool because you actually can see which kind of particles are produced just having a look at your event display. Then you have obviously to run on the analysis to understand and to recognize all of them. There are also background events that are related to other interaction, like the weak interaction, pion decay, and also the negative pion capture at rest for pi minus. So this is a quick overview of our event selection because we needed to select good pions. So the main idea was selecting pions, or at least pi mu e candidates, in the time of flight versus momentum from the beamline information. Then we were rejecting high pile-up events in which you had a multiple matching between the track that was reconstructed along the beamline and the multiple tracks that were reconstructed in the TPC. And also we were rejecting shower-like events that were due to electrons from the beam, and we don't want, in this case, electrons. So after selecting good pions, we had to think about how to measure the cross-section. So in case of a thin target, we all know that the probability of interaction in a slab of whatever material can be measured as the ratio of the interacting and the incident particles. And in case of the thin target approximation, this is linearly proportional to the cross-section. So it is possible, in this case, to extract the pion cross-section as a function of energy, as it is here reported. But the thing is that the area TPC volume is cannot be considered a thin target for the pion interaction. So we had to develop this thin slice TPC method in which we were treating the wire-to-wire spacing of the TPC as a series of thin slab targets. So we were measuring the incident energy from, we had the incident momentum, we were converting into incident energy, and we started following the TPC track in slices, evaluating the kinetic energy at each slice. So, and the information about the energy deposit was actually the charge that was deposited in each wire. So here I'm trying to make it more clear. So you have the wire chamber track that points to your TPC track. You start following it, you get to your first slice, and each slice was representing the distance between each 3D point in the track that was reconstructed in the TPC. So for each slice you ask, is this the end of the track? If not, it means that with this energy, you evaluate the energy of the pion here, and it means that with this energy, the pion was not likely to interact, and so you feel only the incident histogram. So you keep going, following the track, and if it's not the end of the track, you feel only the incident histogram. As soon as you get to the end of the track, so the interaction point, that means that with this energy, the pion is also likely to interact. So you feel both the histograms. So you repeat this process event by event until we went through all the sample, and here we see our the interacting and incident histograms for data and Monte Carlo for pi minus, and there is a quite well agreement. And so finally we take the ratio, as I was saying in a few slides before, we take the ratio of these two histograms and we calculate the cross-section in this wide range of energies, because you actually have different energies that you can analyze. I just want to remind that in this preliminary analysis, the capture and decay processes are currently included in the pion-argon cross-section measurement, and we are currently utilizing data in Monte Carlo to estimate the diffraction and employing methods to remove this from our sample to get to a pion on argon cross-section measurement only regarding the strong interaction processes. So here it is. This is our first measurement of the pion on argon cross-section, and this is, as I said, it's in an energy range from 50 to 1 GeV, let's say, and we evaluate systematic statistical error as well as the systematic uncertainties that are mostly related to the DX calibration on the wires of the TPC. We had also through-going muon contamination due to the muons in the beam, and we can see that it is a quite well agreement between data and Monte Carlo. So we were quite satisfied with that, and we are also still keep working on improving this result. So summing up, I've presented here our first pion-argon cross-section measurement that utilizes this fully automated reconstruction of the interaction in liquid argon. That is this Larsoft framework that is used for all the liquid argon experiments. And next steps for the pi minus analysis will be the treatment of these background processes, as well as investigating the performance of the other auxiliary detectors, beamline detectors, to improve the sample purity. So here we get to my conclusion. From the data side, the results that I've shown are only related to run 1. Run 2 has 5 times more statistics, so we would expect better and improved beam tuning, so we would expect higher quality data. Run 3 is planned for next year, more R&D focus. From the analysis side, there are also other cross-section analyses ongoing on pi+, pion-argon-active channels, kaon and proton interactions, and also from the R&D side, there are ongoing light collection studies that are quite important to combine the information from light and ionization to improve the energy resolution, and wire pitch studies to see the improvement on the spatial resolution for TPCs with different anode wire spacing. So more is about to come from Lariat, so stay tuned. Thanks.
Perfectly in time.
Great.
Thank you very much. Time for a couple of quick questions, if you have. Then I have one, so the 2 questions are already scheduled.
Okay, you briefly mentioned the possibility to constrain neutrino oscillations. Could you elaborate a bit about that? Because you never repeated.
The main topic is that in case of the neutrino interaction, you have to be sure what kind of secondary particles are produced and which was the energy of the neutrino that was actually interacting. So what you see in a neutrino experiment are the secondaries that are produced, and you have to move backwards to see which was the energy of the secondaries, and then you sum up those energies to recover the neutrino energies, as well as you have also to understand which was the flavor of the neutrino. So, for example, the study on the pion interaction is important because pion are highly produced in case of 1 GeV neutrinos, and pions are also very likely to interact. So if you have a pion that, for example, is absorbed and you see only nucleons after some path of the pion, you have to know that these nucleons have to be summed up, and you get to the pion, and then you know that this pion is coming from the resonance channel for the neutrino interaction. So our goal is to give somehow a feedback from the backwards of the study, because what you see in a TPC, it's always like nothing and a smash of particles. So what we know instead is I have a particle, I see how it interacts, and then I can help out in case you want to reconstruct the secondaries that are produced. I hope it's...
But nobody did it in the Fermi lab, the constraint about the neutrino oscillations. Because you produce neutrino, you generate neutrino, so you have more information than other experiments like Ice Cube that...
Yeah, actually, yes, but you know, the neutrino beam is quite wide, so, and also oscillation, especially for the sterile neutrino anomaly, you still have to know which was the neutrino right there and which should be the energies with a better energy resolution than the width of the spectrum of the neutrino produced by the booster beamline. So that was the main idea.
Okay, just a quick one. Slide 27. Okay. Increasing the energy and the uncertainty increases too.
In case of data, this is
data.
Because, yeah.
The error bars.
Yeah, for data we show...
For me, it's not... it's not
this is because we have used the same size energy beams, but actually our beam is less... it has less statistic for high energy. So also another goal of the analysis would be to have not same size binning for the energy, and maybe to merge up higher energies data, because we have actually less events. So obviously the statistical error is big, and this is something that we were thinking about
So
no,
signal
I
to
know that-
noise ratio is constant, but you have less statistics.
Yeah, this is just because of less statistic.
Thank you.
Because the signal to noise ratio, it's actually independent on which kind of channel you see, because you just follow the track and you see how much the charge that is deposited for that event, for that wire, is higher than the noise. And since we are working with that cryogenic environment and also cryogenic readout, you really improve it a lot. So
Thank you very much. So, thank the speaker again.
Thank you.
And we move to the next one. So, Raffaele Del Grande from Frascati. Is it correct? And we have to switch the presentation. I think it's here.
Okay. Good morning. I will speak about the Amadeus experiment, starting from the scientific case, and after I want to show you one of our recent results. Amadeus means antichaonic matter at Daphne, an experiment with unraveling spectroscopy, and works at the National Laboratories in Frascati, which is this facility that is around 17 kilometers far from Rome city center. And the Amadeus experiment focuses on low energy QCD in the strangeness sector. It's performing experimental activity on low energy QCD in strangeness sector. So the question is, why we study antichaonic matter, and more in general, why we study strangeness? Because, as you know, strange quarks are intermediate between light quarks and heavy quarks, and the large difference of mass between the quark S and the UND quarks causes the interplay between the spontaneous and explicit chiral symmetry breaking in low energy QCD, which is responsible of the hadron mass generation of the problem of the hadron mass origin. So one possibility, one way to understand how hadron mass are generated is to study how antichaons changes their mass in nuclear medium, because this provides information on the partial restoration of the chiral symmetry. And in particular, Amadeus is studying low energy K- interaction with light nuclei. For light nuclei, I mean hydrogen, helium, beryllium, and carbonium, in order to clarify some aspects related to how hadrons containing strangeness behaves in nuclear medium. The first point is the antichaon-nucleon attraction, because we know this interaction is attractive, but how strong is this interaction is the problem, and this information will clarify some aspects. The first is the question of the lambda 1405 nature, which is a long-standing open problem in strangeness to nuclear physics, because lambda 1405 is a state which lies only few MeV below the antichaon-nucleon threshold, and it doesn't work with the simpler three-quark model, so its nature is at the moment under investigation. And these are two most discussed models at this moment. The first one predicts the lambda 1405 to be given by the superposition of two states. The first one is mainly coupled to the antichaon-nucleon channel, and the second one is mainly coupled to the sigma pi channel. And the other model that use different theoretical approach predict the lambda 1405 to be a single resonance. Both the two models, however, are not in disagreement with the picture of the lambda 1405 as an antichaon nucleon bound state. So what we can do is to investigate the lambda 1405 state through its decay into sigma pi neutral channels. In addition, another open problem is the quest about the possible formation of antichaon multinucleon bound state, which means if the antichaon interaction with the nucleons is attractive enough, we might expect that it can be bound with 2, 3 or more nucleons. And these states were predicted for the first time by Vicek and after by Akaishi and Yamazaki. These are two possible chaonic bound states. The first one is the K- proton-proton bound state, which can decay into lambda proton or sigma 0 proton final state. Later I will show you how to search for this state through this the sigma 0 proton final state. And the other one is the K- proton-proton neutron bound state, which has other decays. However, the situation for this, for example, for the K- proton-proton bound state is very confused, because these are the predicted value for the binding energy for the width according to different theoretical approach method. And as you can see here in this plot, the theory is not in agreement, and also the experiment that are this one in red measure different values. It seems that these depend from the way you generate this state and how you observe it. So in this topic we need a more precise and deep experiment investigating these states. The second topic of the Amadeus goal, the scientific case, is to extract more data for the hyperon-nucleon scattering, because this is extremely important. These data are extremely important for constructing the equation of state for neutron star in those models in which the hyperon formation is predicted inside the star, but also to estimate the possible gravitational wave signal due to the merging of two neutron stars containing strangeness. Amadeus uses Daphne, which is the accelerator of the National Laboratories in Frascati. Is a double positron-electron collider working at the center of mass energy of the phi meson, which decay with a branching of 50% into a couple of K plus K minus. The kaons are produced with a very low momentum. The momentum is around 127 MeV and a back-to-back topology. Now, Amadeus is at the step 0, which means we are analyzing the CLOE 2004-2005 data set corresponding to an integrated luminosity of 1.74 inverse picobarn. And we have the advantage to use CLOE, which is the detector, and has excellent feature because he has, first of all, a cylindrical geometry, and so he can cover almost the whole solid angle. So we have about 96% of acceptance, and it is optimized in detecting all the charged particle in the energy range we are interested in, and also has good performances in the photon and neutrons detection. In this step 0 of Amadeus, we are using CLOE, the detector, has an active target. this is a section of the Chloe detector in which you can see the Daphne beam pipe. Ooh. Okay. Devo farlo io? Controlello. Okay. So now we are using Chloe as an active target. This is the section of the detector. Here you can see the Daphne beam pipe. This is the electron-positron interaction point where the kaons are produced. And from here, the kaons have to cross all the Chloe materials, and they can interact hadronically with the nuclei composing the materials of the detector. Here I show you this plot in which in this plot there is the number of hadronic interaction versus the distance between the hadronic interaction vertex and the interaction point of Daphne. And as you can see, in the direction orthogonal to the beam pipe, so in this direction. And as you can see, we have a certain amount of events in the beryllium sphere of the beam pipe, a large amount of events in the drift chamber wall, which is composed mainly by carbon, and in the drift chamber gas, which is a mixture of helium and isobutane. So the advantage of using Chloe as an active target are that we have excellent resolutions, but the disadvantages are that the interpretation of the data is very complex because we have different nuclei contamination. From here to now, I will refer to the sigma 0 proton channel to show you what we can extract. The event selection starts from the identification of lambda 1116 from its charge decay into a proton and pi minus. The proton and pi minus are identified through the DEDX information in the drift chamber wires, because if you use the energy in the calorimeter, as you can see, we cut the low momentum particles, essentially. And from this channel, we reconstruct the lambda 1116 with very good resolution. This is the proton pi minus invariant mass, and as you can see, the peak at the mass. The second step is to, once we have reconstructed the lambda, we extrapolated backward the lambda path through its intercept, the extra proton track, and this is the hadronic interaction vertex. For reconstructing the sigma 0, we require also photon signal at the hadronic vertex. And okay, once we selected all the sigma 0 proton events in all Chloe, we selected only those in which the hadronic vertex is located in the drift chamber wall, which means carbon target. So the kaons interact with carbon nuclei and gives the sigma 0 proton in the final state and the residual, okay? This is the lambda photon invariant mass, so our sigma 0 reconstructed. This is the signal. And we have two backgrounds due to the misidentification of the photon coming from the sigma 0 decay. In order to to understand the data we selected, we have to use all the possible processes involved. So we use from the data, we reproduce the background from the data, and from Monte Carlo simulation we simulate all those more probable processes, which are the multinucleon absorption processes, in which the kaon interact with two nucleons bound in the carbon nucleus, or with 3 or with 4, essentially, giving a sigma 0 proton in the final state. Using all these processes, we fit simultaneously all the relevant kinematical variables, which are the sigma 0 proton invariant mass, the angular correlation, the sigma 0 momentum, and the proton momentum. These are the Monte Carlo simulations, and these are the data. From this fit, we isolated and extracted for the first time the probability to have two nucleon absorption processes in carbon giving a sigma 0 proton in the final state. That is the contribution here in red, the two nucleon absorption processes, because as you can see, this is the only contribution which can go to high invariant mass region, so we can isolate this contribution. But also from the fit we extracted for the first time the contribution, the probability to have 3 nucleon absorption processes. After this, we reperformed again the fit, adding an additional degrees of freedom, that is this one in green, due to the possible contribution of an eventual K- proton bound state through the sigma 0 proton decay. The best fit give us a binding energy of 45 MeV and a width of 30 MeV. And from a statistical significance test, we obtained the result of 1 sigma. So we cannot claim the discovery of the state, the measure of the state, but we can set an upper limit for the formation probability. For the future, we want to reuse the Chloe apparatus using target for Amadeus, so dedicated target, and to follow the topic of the scientific case that is almost similar to the previous one. So as a conclusion, Amadeus is now at the step 0, which means we are analyzing the Chloe 2004-2005 data, and we can extract information for all the topic of the scientific case I explained before. Now we have a lot of ongoing channels in analysis, and 3 are completed. I show you today only the first one, the sigma 0 proton channel, from which we extracted for the first time the 2 and 3 nucleon absorption process probability, and extracted an upper limit for the bound state, for a kaonic bound state. For the future, we want to ask for an Amadeus dedicated setup. Thank you.
Time for a couple of questions. Can we change the people who make the questions? Okay, so no, it's okay. So we have. Then I have one. So we repeat.
I'm just curious to know something you mentioned in the slide where you said this could be a motivation, an astronomical observation. what is a quark star? Well, you mentioned a series of, well, neutron stars are well known, and exactly that to the last one, quark star.
Yes, that this imaging was taken by a presentation of Alessandro Drago and Ignazio Bombaci, which are two experts in studying exotic Newton stars. And quark stars means that at some densities and in some condition they uses a lot of how to say, a lot of assumption, and in certain condition they expect to have an inner core of the star which is given by quarks. I don't know exactly the confined, I don't know exactly, but it seems to work. I don't know.
Any other question? Oh, yes.
I also have a general curiosity related to this. What does hyperonic matter stand for in general?
Okay, hyperonic means matter in which you have hyperons, so baryons containing strange quark, essentially. Yes, so lambda, sigma, and that's this is. The problem is that they need more data on the hyperon-nucleon scattering, so lambda neutron scattering, lambda proton scattering, sigma 0, also omega and other hyperons. So we can provide this data because we have Daphne, which is a unique source of antichaons with very low momentum, so we want to use Daphne. Okay.
Anyone? No? I have one curiosity while we switch the presentation. The degree of purity of the targets. It has, I think it has an influence on the outcome of the whole collision processes. And
yes, we performed a lot of studies, Monte Carlo simulation, to understand the contamination from nuclei, and the problem is that the wall is mainly composed by carbon, so if we restrict the cut on the radial position of the vertex, we are sure we are considering only events in carbon, for example, for the wall. But the problem is that we reduce the statistic, because of course if we consider a very thin region, this is... okay.
No problem. So how much can be the target material or the sensor material contaminated by other?
Less than, we calculated less than 5% with our cuts.
So we are in the percent scale of purity of this.
Yes.
Okay. Thank you very much. Thank you, speaker, again. And we move to the last talk because the invited talk is shifted after the lunch. And welcome to Elisa Incani from Cagliari.
Thank you.
And you talk us about production in lead collisions, the muon production. So I just need to make it disappear, not your presentation, just this. Just this. Okay.
Okay, thank you. So I'm speaking about a new experiment that studied the muon production in lead collision at 20 to 160 GeV per nucleon in the laboratory. The idea is to study the quantum chromodynamics per diagram, the transition region. Okay, the quantum chromodynamics is the theory of the strong interaction between the hadron, quark, and gluons. This theory describes a phase transition between the hadron matter, where we have quark and gluons confined, and the quark-gluon plasma, where we have the quarks and gluons deconfined. We can describe this transition using a diagram, temperatures versus baryon chemical potential. This means the baryon density, the number of the baryons minus the number of the antibaryons. And the theory describes a crossover transition at high temperatures and low baryon density, and a critical point. After that, moderate temperatures, large baryon density, a first order transition. This means that in this phase we can have the mixed phase between hadron and quark-gluon plasma. In this transition, we can observe also the presence of the chiral symmetry, the symmetry of the strong interactions, where we are in the confined phase, the spontaneous breaking of the chiral symmetry. This means that the quarks acquire through dressing with the gluons and an effective constituent quark mass. And in the confined phase, we have the chiral symmetry restoration, where the quarks lose this additional mass. So we have the original mass that we have in the Lagrangian of the quantum chromodynamics. To describe this, we can observe this plot where we have the mass of the quarks. In yellow, we have the mass due to the spontaneous breaking of the chiral symmetry. We can observe that for the light quarks, we have that this mass is bigger than the other one. So this means that the dominant part of the visible part of the universe, the mass for this, for the visible part of the universe is coming from the spontaneous breaking of the chiral symmetry. So the idea is to study the confined phase in the laboratory using the relativistic EV-ion collisions. With the collision of the two EV-ion, we can obtain a quark-gluon plasma phase for a short time, but enough to obtain the quark-gluon plasma phase. After this phase, we have the hadronizations, and then the freeze out, where we have the hadrons that we can detect with our detector that give us information about the previous phase, the quark-gluon plasma. So the idea is to study the phase diagram, and the high temperatures in this region where we have the crossover is already studied by older experiment like NA6T, and the experiment that run now in the LHC, like Alice experiment. But in this region where we have moderate temperatures and high baryon density, we haven't done yet the experiment. In principle, we would like to study the existence of the critical point at the first order transition, how the chiral restoration change the mass spectrum. The idea is to have a low energy experiment so we can use, for example, the RIC accelerator, SPS, or FAIR. Our idea is to use a new experiment. The name is the NA60 Plus. Is detect the muon pulse production via beam scan energy, the energy between 4.5 and 70.3 GeV in the laboratory to 160 GeV per nucleon, and use the CERN SPS at the CERN. So why we would like to use the leptons? Because the leptons is emitted at all stages of the evolution, and we have the evolution of the collision. Before we have the nuclear-nuclear collision, the leptons are emitted like Drelian open char pairs. For our study, the physical background, we can observe in light the mass spectrum. This contribute to coming in the high mass region. Then we have the quark-gluon plasma that that we have the lepton coming from the thermal quarks and quarks annihilation is giving us information about the deconfinement. We can find the intermediate mass region. Then we have the hadronization. For example, we can study the Mason's law and A1, that the modification give us information about the chiral restoration. It's also in the middle intermediate mass region. And then we have the freeze out, so we have the hadron that decay in muon pairs in the low mass region that for our study are background. Okay, I can study the chiral symmetry restoration. So we can use the mesons. In our case, the rho and the A1. These are the chiral partners mesons. So this means that are the similar quarks, but different in quantum number. And in the vacuum, there are different mass. The rho 770 MeV, A1 1270 MeV. And the chiral restoration should be have the similar mass. We can have two possibilities: the dropping mass at the top and the melting resonance. So I can study this using the muon pairs. The rho decay into muons, and the one cross with the pi 0 and decay into muons. We have the previous study of the muon mass spectrum in the intermediate mass region, the Na60 GV, that collected the data at full SPSS energy. But we can observe that it is impossible to observe this resonance law and the A1 mixing because we have the quark-gluon plasma is predominant in this region. So to study the chiral symmetry restoration, you need an experiment that runs at lower energy. Another interesting topic is measurement of the caloric curve. To study the caloric curve, you need to evaluate the temperatures of a quark-gluon plasma. We can study using the intermediate mass region. I fit this region using this formula. The NN60 is the previous experiment that study the temperatures found at 200 MeV. But to study the caloric curve, you need study the temperatures with energy scans between 4.5 and 70.3 GeV, and for such a possibility plotting of the temperatures. The caloric curve to study the quantum chromodynamic space diagram was never determined so far. So why would you like to use this CERN SPSS? In principle, we have a different facility to can study this topic. But, for example, we have the FAIR facility, CIS-100, but use the energy region between 2 and 40.5 GeV, and maybe we haven't the confinement, so we can use this. And then we have the NICA and the leak at the lower energy, but the region of study in the energy is okay, but the intensity of the beam is too low for us, our study, because we need a lot of statistics. So the idea is to use the CERN SPSS because I have a high intensity beam and cover the interesting region of the energy. So how can you detect the muon pairs? The idea is to use a muon spectrometer, so spectrometer after the hadron absorber. The hadron absorber stop all hadrons, and after this we have just the muons. We can, using the detector, we can determine the momentum and the energy of the muons. But the hadron absorber, degrading our tracks, so we have energy loss fluctuation and multiple scattering. So we would like to have higher precision. So the idea is to use a silicon vertex detector before the hadron absorber. Then we take the tracks before and after the hadron absorber and match the two tracks to obtain the muon tracks with higher precision. With the vertex spectrometer is useful also because we can detect all the hadrons and we can evaluate the multiplicity, then to give us information about the net density energy. So this is Na60 plus. We have 4 muon tracking stations. We are thinking to use the GEM detector and asteroid magnet with a 0.75 Tesla meter field integrate at 1 meters. The hadron absorber composed by graphite, beryllium, oxygen. We have this hadron absorber study for the 40 GeV per nucleus collision. The idea is to increase this hadron absorber when increasing the energy, but with the similar sigma to background ratio. Then we can observe another muon wall that stop all hadrons, and then we have the trigger station. So to be sure that the tracks that arrive in this point are muons. We have the vertex spectrometer, the very important detector, because it gives us the more information about the momentum energy. We have, for the moment, 5 stations of hybrid pixel, but we are studying to increase the number of the stations, also to use another kind of the pixel. Then the main experiment goals would like to study so energy, like the collision at different energy, and to have enough statistics to can isolate the lepton spectrum in the intermediate region to study the temperatures and also the killer restoration. So we'd like to study to have enough intensity beam to collect in just 50 days in time the statistic of upper energy. So this is a data sample at 40 GeV per nucleon that we have simulated. We can observe, in blue, the opposite sign pairs, the muon spectrum. In red, we have the signal after the background subtractions. And in blue, we have the background. To compare, we can observe the old experiment in 60 at higher temperatures. With the new setup in SPS, also in our detector, we can increase the statistic of a factor by 100, but we have a similar background ratio, but we can increase the mass resolution. For example, we can observe the omega. We have a mass resolution between 10 50 MeV, and the whole experiment, the mass resolution was 23 MeV. This is a mass spectrum after the background subtractions. In yellow, we can observe the mass spectrum. We have all contribute. We can observe that thermal radiation is isolate. We can subtract the Drellian open beauty for our study. And also the resonance are visible, so we can subtract for our study. Then we have the mass spectrum after the acetone correlation. In red, we have the mass spectrum coming from the thermal radiation, useful to evaluate the temperatures. We have evaluated this temperature, 163 V. We can observe we have the MeV precision, so it's very good opportunity for our study. And is it possible to isolate this region? Also, in green, we have the low and A1 mixing. As we can observe that it's possible to isolate, so should be studied the killer symmetry restoration. So to conclude, Na60 Plus is a new pixel target experiment at the CERN CPS. It's dedicated to study using the muon pulse production with high precisions over in different energy range. For the high intensity quality beam, the idea is to use it's better to use the CERN CPS. We would like to study the dileptons because our ideal probe because are a producer in all stages of the evolution, also because give us information, the primary information of the quark-gluon plasma, because the dilepton doesn't interaction with the system because are not a strong interaction. We have a lot of possibility of urban N60. I show the first order phase transition, so the first measurement of the caloric curve, the Killer symmetry restoration, the first measurement of the law, and A1 mixing modification. But we would like to study other things like DJ suppression and open channel production that give us also information about the Killer symmetry. Thank you.
It's 5 minutes.
Oh,
You are right. No, thank you very much. Thank you very much. Because okay, so we have a little more time for questions, if you have any.
Yeah, in the beginning of the presentation, you showed the complete phase diagram for the quark matter. I see that it has a striking resemblance with the phase diagram for correlated oxide materials with some ordered phases at the bottom and conductive phase at the top. Could you please give some qualitative descriptions of the various phases that populate these phase diagram?
Okay, the hadron gas is the hadron matter that we have. We can observe that in the first part where we have the high temperatures, we can is the part similar at the early universe, and then. Okay, where we are the quark plasma, where the quarks and gluon are deconfined. We are the color superconductivity is the region where the quark and gluon are not like deconfined, but with also the mass due to the spontaneous breaking of the chiral symmetry. Like this, also the color flavor like this. We have yes, the quark and gluon are not hadron matter, but is deconfined, but take the mass due to the spontaneous breaking, and the name is superconductivity because the matter is similar to the superconductivity in the matter and the ordinary. Sorry.
Thank you. This was a very good question because this shows the multidisciplinarity of this meeting. So from solid state to
yeah.
And that question triggered my curiosity. If I can ask you, what happens in the tripole point where the three phases meet?
Yes, like
when the yellow curve of superconductivity meets there. What happens? Is there any interest in physics?
Yes, but we have to study this region because
so still uncovered.
Yes, we have a measurement just in this region with the LHC and other experiments. But this region we haven't experimented, so this is to.
In theory?
In theory, we have a second order transition, but the theory is not very clear because we have very short information about this.
So to a profane like me, that point seems to be interesting. Is it real? Is it actually interesting?
Yes.
Okay. Thank you. Okay. Anyone? No.
My question refers also to this triple point transitions, and you mentioned the possibility to measure the raw A mass. Which is the role with the chiral restoration? Which is the role of this?
Sorry, I don't understand.
Which is the role of the mass rho A you mentioned? In the last, yeah, well, you can take the last slide.
Okay, sorry, I don't understand.
In the possibilities of, yeah, you can take the last slide, the number 16, maybe. Possibilities offered by an A60+, Kira symmetry restoration, first measurement of air A mass.
Yes.
What
okay.
is the role of this raw A state with the Kira restoration? That's my
Because Rho and A1 are two chiral partner mesons, so they are the similar quark composition. So you think that same quarks mean same mass, but it's not a pair. In the nature, we have the Rho have a mass of 770 MeV, and I1 1270 MeV. So the difference is a lot. So we have the study, the theory that describes that is the differential is due to the breaking of the chiral symmetry. So we think that in the confinement we have the chiral symmetry restoration. So we think that we have the similar mass. So we can find in the confinement the similar mass. We can understand how the chiral symmetry, because we are not. If, for example, in this plot I show the two possibilities, we know how the how we have the restoration, how change the mass spectrum. We don't know yet.
Thank you.
Thank you.
No other questions? We can close the session. Okay. So thank the speaker again, please. Now, thanks to the speaker, we saved some time. So we go to lunch now, and we wait for you at 2 p.m. here, because the invited talk of this session is shifted after the lunch, and then the last session of the conference will start. See you later.
Hello everybody. We start with the next session that start with the invited talk. We switch from the program. And I present you Andrea Giachero that comes from INFN and Milano Bicocca. He works on nuclear physics, detector, rare event experiment, neutrino mass experiment. He published several papers on these topics, and it's a pleasure for me to introduce you.
Okay, thanks for the nice introduction, and thanks the organizer for this invitation. Okay, in this presentation I'll talk about how to measure the neutrino mass with by using micro and macro low temperature calorimeters. Okay, so from the oscillation experiment, we know that the neutrino is a particle with mass, and there are 3 Flower eigenstates and 3 mass eigenstates, and the neutrino can oscillate from a flower to another with this probability that depends on the energy of the neutrino and on the distance between the neutrino generation and the neutrino detection, where this parameter is the difference of the square of the mass eigenvalue, sorry. So this depends on the fact that the neutrino has mass. The oscillation experiments are sensitive to the difference of the neutrino masses, but are not able to give information to the hierarchy of these mass eigenvalues. So, compatibility with in according with the measurement of the oscillation experiment, and here are listed some of these. There are 2 hierarchy allowed, the normal hierarchy and the inverted hierarchy. So a way to study a neutrino, to measure the neutrino mass and to search which is the real hierarchy, there are tools different to neutrino oscillation, alternative to the neutrino oscillation. These 3 tools are the constraint from cosmology, where the observable is the sum of the mass eigenvalues, the neutrino double beta decay, where the observable is the effective Majorana mass that depends on the rate of this decay, and the direct neutrino mass determination, where the observable is the mass of the neutrino measured study a simple beta decay or a simple electron capture. The cosmology has the problem that suffer of model dependency. The neutrinoless double decay is model dependent because computation of the nuclear physics, nuclear element, matrix element, and also the space factor, while the beta and point measurement is the only one that is total model independent. In this last, the idea is to measure the teeny deformation at the endpoint due to the presence of the neutrino mass. This is the endpoint. This is a simulation. with 0 mass and with a mass of 1 eV, and this is the deformation. Measuring this deformation is possible to put a limit on the neutrino mass. To increase the sensitivity on this parameter, the neutrino mass, one needs high statistic at the endpoint, and this is possible with isotope, with a very low endpoint energy, and using a source with a high activity and high efficiency. So isotope with low Q value and short half-lives are preferred. There are 3 isotopes studied. One is the tritium, and the other 2 are the rhenium 187 and the holmium 163. This first used is used in experiment with spectrometers, with huge spectrometers, while these last 2 are used in low temperature microcalorimeters. In this case, the rhenium, the holmium decays on excited state of these 2 isotopes, and with the microcalorimeter it's possible to measure all the excitation energy, but the neutrino one. That is the parameter you want to measure. The other tools is the neutrinos double beta decay. The neutrinos double beta decay is a second order transition. Is allowed when the beta decay is suppressed. Can happen only if a neutrino is a Majorana mass, and is forbidden by the standard model because the leptonic number is not conserved. This is the half-life of the decay. This is the phase space factor, the nuclear matrix element, and the effective Majorana mass. Studying this parameter is possible to have information on the absolute scale and also on the neutrino mass hierarchy. The experimental signature is a monochromatic energy at the endpoint. This is the sum of the energy of the 2 electrons emitted. And close to this monochromatic line, there is the endpoint of the 2 neutrino double beta decay. This is a standard model allowed, and this is an available source of background. So detector with excellent energy resolution are needed. The experimental sensitivity is given by this formula. So to maximize the sensitivity is needed a high efficiency, that in case of microcalorimeter is almost 1, a high isotopic abundance of the isotope you like to study. Only the tellurium 130, this is greater than 10%, so, and other candidates need enrichment. A high exposure. At the present, the mass of this kind of experiment is around 2 kilogram, 200 kilogram, 300 kilogram, and to totally cover the inverted hierarchy region is needed tons of this isotope. Is needed a good resolution and of course low background in the region of interest, and this is possible using underground location, performing a very stringent material selection, and applying reactor techniques. The choice of the isotope, it depends on in order to choose the best isotope, one has to take into account that the Q value must higher than the gamma and beta lines that could increase the background, an isotopic abundance, the compatibility with the detection technique, and the selected isotope must to maximize the phase factor, the phase space factor, and the nuclear matrix element. These are the common isotopes used to study the neutrino-less double beta decay, and in blue are reported the isotope compatible with the with low temperature macrocalorimeter. So, what is a low temperature detector? The temperature detector is a detector that are able to transform the particle interaction in a temperature rise. Was proposed for neutrino physics the first time in 1984, and here are reported some picture. This is a informal bolometer to measure the CMB. Is informed as microcalorimeters to study the beta decay. It is informal macrocalorimeter to study the neutrino-less double beta decay. So, how work and calorimeters, low temperature calorimeters? So, when the particle interact with the absorber, there is a rise in temperature that depends on the energy and on the specific capacity of the absorber. To maximize this effect, one needs an absorber with very low thermal capacity, and for this reason it's better to use superconductors or dielectrics where the capacity follow the Debye law. And is also needed a very low temperature in order to minimize this thermal capacity. So the typical temperature is below 10 millikelvin. The limit on the resolution, this is an important parameter for this kind of studies, is only limited by the statistical fluctuation. It is the theoretical resolution. The release time is proportional. It depends on the thermal capacity and on the conductance. No, sorry. Thermal capacity and on the conductance between the cryostat and the detector. So here are reported several examples of application and configuration. Macrocalorimeters are used for the study of the neutrino-less double beta decay, for the study of the dark matter, for the study of the single beta decay, and also for X-ray application for astrophysics, but also for synchrotron and X-FEL lights. The temperature rise in a calorimeter is measured by a temperature sensor. There are several temperature sensors. A temperature sensor is a sensor that is able to translate the the temperature rise in a variation of an electric signal. Here are reported three of the main temperature sensors used. Semiconductor thermistor, where the rise in temperature is translated in a variation of resistance and in a variation of signal. The transition edge sensor, this is a superconductive sensor. Also here the variation in temperature is transformed in variation of resistance. Since the resistance is very low, a low temperature superconductive amplifier is needed. The third one is the metallic magnetic calorimeters, where the sensor translates the temperature rise in a variation of the magnetization. Also in this case, the readout is performed by a superconductive amplifier. Here are reported some resolution obtained with this sensor. and for macro and micro calorimeters, and the resolution is around 1 per mile. So this kind of detector are characterized by a very high resolution. For measure the neutrino mass with the study of the endpoint of the nuclear beta decay, the first isotope used was the rhenium-187 in form of metallic rhenium and in form of dielectric rhenium, and with anti-determistor in two main experiments, the Mano experiment and the Mi-beta experiment, the first in Genova and the second one in Milano. This is the SketchUp of the configuration. So here the sensor, this one and this one, connected with the rhenium metallic crystal in this case, and the silver parenite in this other case. Here the result. So the best, these two are the best limit on the neutrino mass obtained with microcalorimetric approach, around 26 eV and 15 eV, by using this quantity of uranium, the quantity reported here and here. So this is not enough, because the goal is to try to enter the inverted hierarchy region. To do this, one needs 0.1 eV for the sensitivity on the neutrino mass. So the idea was to create an array of rhenium pixel, a large array. The idea was to develop an experiment with 100 pixels of rhenium, but we had a lot of problems. So at the same point, we decided to change isotope, moving to the holmium-163 that was proposed for the first time in 1982, but only recently the technology, the low temperature technology, allowed to design and develop an experiment by using this isotope. The idea is to measure the entire energy released at the endpoint. Like this is an electron capture decay. So, like in the beta decay, the idea is to measure the entire energy released, except the neutrino ones. The endpoint this endpoint is measured with penny trap mass spectroscopy, but no calorimeter measurement with an autostatistic at the endpoint is performed. So an experiment that uses this kind of isotope as with first goal to assess the Q-value with a long calorimetric measurement. The Q-value is quite low, and the activity is low, so high, sorry. So the holmium detector is not needed, and so is not needed a crystal compound with holmium, but it's possible to implant the holmium-163 in any suitable microcalorimeter absorber. This is the spectrum, the continual Bright-Wiener, a continuum with Bright-Wiener shaped peaks, one for each electron capture. At the endpoint is shaped like the single beta decay. One important feature is that this kind of spectra is totally self-calibrating. This is the statistical sensitivity on the neutrino mass by Monte Carlo simulation. So in order to reach the 0.1 eV, one needs an high resolution, a fast response in order to avoid pile-up events, and a very huge amount of pixels. So to reach this sensitivity, one needs 10 to the 18, 17 events, acquired events. There are 3 experiments that are studying in the near future the holmium. One is the HECO experiment in Germany. The second is the NUMEX experiment in US, and the last one, that is the youngest, is the Holm experiment that will study the holmium 163 in Italy. So some preliminary result from this kind of experiment. HECO use metallic magnetic calorimeters. The holmium is produced by the ELL reactor in Grenoble and implanted at the Isolde CERN facility. The activity per pixel is around 0.2 becquerel per pixel, and 2 pixels simultaneously were measured. The spectrum is reported here. This is presently the most precise spectrum, holmium spectrum, with a resolution of 7.6 eV and a rise time of 130 nanoseconds. The future development are a 1 kilobecquerel experiment with a resolution of 5%. And this means a sensitivity around, for the neutrino mass, around 20 eV after 1 year. In the case of the NUMEX, the sensor are transition edge sensor. The gold is embedded in the absorber using nanoporous gold. The pixel, the activity per pixel is 0.1 becquerel. This is the spectrum obtained after 40 hours of measurement. And the future development is an array of 4 times 1024 pixel array for a total of 1000 becquerel per pixel. This means a sensitivity of 1 eV after 1 year. The youngest is the Holmes experiment, with the goal to prove the potential for a future technique that could be used for a future megapixel experiment, and at the same time to have a sensitivity on the neutrino around 2 eV. And also to assess the Q value with a long calorimetric measurement and to assess systematic errors. The sensor are transition edge sensor with the holmium implanted in gold absorber for a total of 18 microgram of holmium. That means an activity of 300 decay per second per pixel. The target resolution is 5 eV and the rise time around 10 microseconds. The mid-term demonstration will be composed by 64 channels, and the final experiment will be composed by 1024 channels. This is the first measurement of the developed pixel, obtaining a resolution of 5.2 eV at the manganese K-alpha lines. It is the rise time, with a rise time around 15 microseconds. So the pixel developed fulfill the requirement for Holmes, and the next year will be start the implanting test and the development of the detector, and in 2018 the measurement will start. So this is the status of the sensitivity. This is the actual spectrometer limit. Holmes and the other experiment will be placed here, but to reach the inverted hierarchy, a next generation of megapixel Holmium experiment will be needed. For measuring the neutrino-less double beta decay, one of the used crystal macrobolometers are the tellurium dioxide, where the isotope is that is embedded in the absorber is the tellurium 130, that it has a very high isotopic abundance, a Q-values almost above the natural gamma background and below the natural alpha background. The tellurium dioxide is easy to grow in big crystal with low radioactive contamination, because the background is very important. And the sensor used are germanium crystal doped by thermal network, the NTD germanium thermistor. This is the history of the double beta decay with tellurium dioxide from Milano double beta decay to core experiment. It will be the biggest macrocalorimeter experiment ever built. One of the intermediate step is the core experiment. This is the first tower of core used to test all the procedure that have been used also for core, and it ran from the 2013 to 2015. This is the result. So no evidence of neutrino beta decay. A background in the ROI 6 times better than the Cuoricino 1, that is another intermediate experiment, with a sensitivity combined with the Cuoricino 1 equal greater than 4.02 times 10 to the 24. That means a neutrino limit in this range. The next step is the core experiment. This is composed by 19 towers like the Core 01, and one important thing is the resolution obtained in Core 0, that is 5 keV. This is the target for Core. A background around 10 to the minus 2. And the idea is to reach this sensitivity in 5 years. That means a sensitivity on a neutrino mass in the range between 50 and 130. This means this limit, so very close to the inverted hierarchy. So in conclusion, the study of frontal subject neutrino physics required the use of frontal detector. The energy resolution, in the two approach, the study of the endpoint and the study of the neutrino double beta decay is very important, and low temperature micro and macro calorimeters today are a major technology to push down the neutrino limit, the sensitivity limit on the neutrino mass. Thank you.
Okay, thanks, Andrea, for your presentation. We have time for one or two question or comment if you want.
Hi. Can you summarize the comparison between the constraint on the neutrino mass between the isotope revelation and other neutrino experiment like IceCube or Amanda or this kind of?
I don't know if IceCube can measure the neutrino mass.
Well, constraint at least on the or others that you are aware of.
No, I don't know. IceCube can measure the energy of the neutrino, but I don't think it's sensitive to the mass. Can put no, I don't know. No.
But there are constraints on the neutrino mass. It's also coming from other collaborations like the Japanese one and Antares and all the other communities that are not using calorimeters and isotope decay.
Because the only
you're probably better.
The only
in
three
the
approach sensitive to the mass is
coming from that formula that you wrote in the first slide with the probability transition.
So
probability.
the IceCube can measure neutrinos from galactic sources, so can put a limit on CMB neutrino. I don't really know how to relate IceCube measurement in this. I don't know.
The second question is, you mentioned in order to get the sensitivity around 1%, 1 per mile, you need something like 10 to the 18 events.
Yes.
How, in average, how much time does it take to get how?
Okay.
This,
to get this sensitivity, one needs at least a megapixel array for 5 years. Because the 3 experiments I mentioned de facto are demonstrator, because the best limit they can achieve is around 1 eV. That is greater than the Catherine sensitivity. The Catherine, that is this big mass spectrometer in Germany, will reach 0.2 experiment. But it will be the last one experiment, because it's not possible to increase the resolution, because one should increase the dimension of these spectrometers that now is 22 meters, and is not possible. So the only way is to use a microcalorimeter, but with a number of pixels very large. And this calorimeter have to work in parallel. So another problem is the multiplexing. And for this reason, we are developing a multiplexing system based on RF techniques in order to multiplex channel like in telecommunication, in order to minimize the bandwidth needed.
Okay, if there are any other comment or question, I move to the. Thanks again, Andrea, and I move to the next session.
So we are now going on with the last session of Matter of Physics, and the first talk is from Matteo Puviani. He is from the University of Modena and Reggio Emilia, and the talk is periodically driven interacting electrons in 1D, a many-body Floquet approach. Thank you very much.
So good afternoon to everybody, and thank you for the introduction and for the opportunity of being here to talk about the work that I'm doing during my PhD student with my supervisor, Professor Franca Manghi. And so that's the title, and this is the talk overview. So there is an introduction to the system that we studied. So there is also some theory, the theoretical framework that we studied from, and the theory that we developed. Then there are some results and some remarks related also to the theory both and the results. And finally, some summary and the outlook for the future perspectives. So let's start with introduction. We studied, we can start from out of equilibrium systems. We know that we can control and tune properties of matter thanks to driving the matter out of its equilibrium phase. And this can be done in different ways, and there are already some interesting results considering out of equilibrium systems, such as, for example, considering a homogeneous laser field applied to a two-dimensional lattice, such as, for example, graphene, we can control Dirac points, so create and move them. And this is a theoretical result. Another one is the opportunity of control the phase states and to induce phase transitions, topological phase transitions in a one-dimensional chain, but also to induce superconductivity thanks to the application of light to a system. So out of equilibrium systems are important by themselves. But, and this is a class of materials, of systems that are important and that we considered. But on the other side, we also consider correlated systems, which means that there are materials where electron-electron interactions are very important and they cannot be neglected. And of course, electron-electron interaction occurs through the Coulomb repulsion of their charges. And actually, in most solids, we can map the problem of electrons plus the interaction with each other, so their interaction cloud, to an effectively non-interacting system, which is composed by quasi-particles. So we can substitute electrons and their interactions with quasi-particles, and the problem is effectively non-interacting. But there is an entire class of materials where this cannot be done, or at least not properly. And for example, these are transition metal oxides, and they are very important materials. In particular, they're very fashionable nowadays because they show some interesting properties and features, such as, for example, high temperature superconductivity or magnetic properties or metal to insulator transition. But to study, it's difficult to study correlated systems, in particular in a true many-body, with a true many-body approach, so considering all the electronic configurations. But it's even impractical to solve the exact problem. First, because we cannot solve exactly mathematically the partial derivatives equations that rise from the interactions between electrons. And moreover, in materials, we have billions and billions of electrons. For example, order of magnitude 10 to the 23 for centimeter cube. So this is quite challenging, and actually it can be done through some approximations and the development of models to describe them and to study them. So let's see the theoretical framework. So we go back to the out of equilibrium systems, and in particular we consider periodically driven system. With this expression we mean system, and in particular we consider one-dimensional linear chain to test and to develop our theory. And under the influence of a time-periodic external field, such as, for example, vector potential of a homogeneous laser field, so constant in space, applied all over the infinite linear chain, and so it's a monochromatic light with a definite frequency and a period associated to that. And in these conditions, the electrons in the linear chain, rather than behaving like just bare electrons, they interact with the photons of the laser field, forming photon-dressed electrons. So they dress themselves with interaction with the photons to form these quasi-particles. And in order to describe this kind of system, we used Fouquet theory, which is quite fashionable, in particular nowadays. And we know that to describe these systems, we should solve the time-dependent Schrödinger equation, where the time-dependent Hamiltonian contains the time dependence which is due to the external laser field, so which is periodic in time with the same periodicity of the laser field. But thanks to Fouquet theorem, which is nothing but a block theorem in time domain, we can write the solution, which is the wave function which describes the electrons, as a factorization of this kind. So we have a quasi-particle wave function which contains the time periodicity, which is related to the external field, times a factor which contains instead the electron quasi-particle energy, which is this E alpha. And of course, the quasi-particle wave function, being periodic in time, can be developed in a Fourier series, and each term, of course, this is an infinite summation, and each term has an index, which is a Fourier index. It's also called Fouquet index, and there is an intrinsic, for each term, the intrinsic time dependence, which contains the photon energy. So we take into account at this level of the interactions with any possible integer number of photons. And thanks to this writing the solution, we can define the Fouquet operator in this way, so with the Hamiltonian and the time derivative. And in this way, we can map the time-dependent Schrödinger equation into a time-independent Schrödinger equation, which is an eigenvalue equation for the quasi-particle wave function. And the eigenvalues are the Fouquet quasi-energies. And I make you notice that these energies are defined actually up to multiples of the photon energies. And this means that, of course, we have infinite replicas of the energies, of the energy levels, according to the absorption or emission of any possible number of photons. And it depends with the interaction of the external field, with the external field. So we can apply this theory to a very simple modem, for example. Without any kind of interaction, we can use, for example, a tight binding Hamiltonian, where the kinetic energy, we take into account only the kinetic energy, which is a single particle term, so we neglect for example, in this, at this level, the interactions, the Coulomb interaction between electrons, and of course, being present also a laser field, the kinetic term is time dependent, and in particular the static term is modified by this exponent, which contains the vector potential, which is periodic in time. And then substituting this matrix in this operator in the previous form, we can define the Fouquet operator, and provided a basis, which can be, for example, a local basis. We can calculate the Fouquet matrix elements, and diagonalizing it, we can obtain the Fouquet eigenvalues. For example, this can be done quite easily for a linear one-dimensional chain, and we obtain this quasi-particle band dispersion. So we can see that, of course, this is a metal because there is this quasi-band, this quasi-energy band which crosses the zero level, which is the Fermi level, and then we have all the replicas according to the net absorption of 1, 2, or more photons, or the emission of them. And here I highlighted the zero mode, and of course this is intended to be infinite in energy and periodic energy, of course. And instead, on the other side, as I told you before, we have correlated systems. In order to describe correlated system, we use the Hubbard model. The Hubbard model is the standard model for to describe correlated electrons, and the Hamiltonian associated to this model is characterized by the kinetic energy term plus the potential energy term, which takes into account of the repulsion of electrons when they are on the same side of the lattice. So this is the true many-body term, and here we are in starting conditions. So this is just for correlated electrons and correlated systems without any field. And in this case, we can look at the configurations. For example, for two sides, we have 4 configurations, and these are represented here. So this is at half occupation and fixed spin, and these are just slated as they have to be intended as slater determinants. But then we can increase the number of sites, and for example, for 4 sites, we already have 36 configurations, and I just put them, some of them here. And growing the number of sites, also the number of configurations grows up quite quickly. And for 20 sites, which is quite a small number compared to the realistic systems, we already have 10 to the power 10. Oh, sorry, 10 to the power 10 configurations. So it seems that we have a problem because we cannot solve exactly quite easily these kind of problems, and in particular even bigger problems. But we can, as I've shown you before, for example, or 6 sites, it's affordable, okay, also for a laptop. But we also have a solution, and the solution that we consider is provided by cluster perturbation theory. So we can, it is based on the exact diagonalization for a small cluster, so we can compute all the many-body energies for the system which is composed by a small number of atoms, and then embed it with the embedding procedure in the infinite periodic lattice. And in this procedure, we only consider hopping, so no correlation, because the correlation is just on-site, as we want to take into account of the Hubbard correlation, so short-range Coulomb interaction, and so only the hopping one is considered here. And actually, in practice, this is done through the Green's function formalism. So we calculate the many-body Green's function for a cluster, and we embed it in the infinite lattice in order to compute the many-body Green's function for the lattice. And so this scheme, we calculate with exact diagonalization the energy levels for just a cluster which has the same symmetry of the infinite lattice. Then we compute the Green's functions, so the propagator, which is related to this system. We perform some approximations on the ground states. So at this level, we neglect single particle excitations, and then we embed it in the infinite lattice, considering nearest neighbor hopping terms. So we end up with a Dyson-like equation for the Green's function, and out of that we get the lattice Green's function, and then we can compute the spectral function, so the energy band dispersion for the Hubbard model. And for example, it is well done, and for the infinite one-dimensional lattice, if we do not have correlation, of course, we have just a metal state, which is this cosine-like band dispersion. But then as we switch on interaction, so U equal to 1, a small gap opens. Of course, I mean, this gap is quite small also because of the scale, but then increasing the Hubbard term, so increase the correlation, the electrons tend to be frozen at their sites, and therefore the gap also increases. So now we have 2 theories, which is on one side an interacting theory, which is the Hubbard model plus the cluster perturbation theory for static systems and even infinite lattices. But on the other side, we have Floquet theory, which works fine for out-of-equilibrium systems, but non-interacting ones. So it's valid only for, let's say, a small, non-interesting class of systems. And then we can unify them in order to have a new theory, which is an interacting Floquet theory, in order to take into account of both the interactions between electrons and the interaction with an external field, such as a laser. So that is what we did. So we consider an infinite one-dimensional chain with interacting electrons and an external laser field. We considered, first of all, the modified Hubbard-Hamiltonian, which is a Floquet Hubbard-Hamiltonian. So we have the Coulomb energy potential and the kinetic energy, which is modified according to the interaction of electrons with the external field. So with the addition of the vector potential. And so we calculated analytically the cluster Floquet-Green's function, where we also have conservation of energy due to the photons exchange. And this is true for a cluster, for example, for two sites, which can be done quite easily. And then we have to extend this thanks to the cluster perturbation theory, which is used in this case for out-of-equilibrium systems, to calculate the lattice-Green's function, which is a Floquet-Green's function in this case, because we do not have only electrons, but we also have photons. So we also have to take into account of the photon exchange during the propagation of electrons in the material. So at the end, we can calculate the spectral function and have the band energy dispersions, or at least the quasi-energy band dispersions, which are related to the quasi-particles, which are photon-dressed quasi-particles. So let's see the results. For example, at high frequency, nothing actually really interesting appears, because we still have a gap, and here the Hubbard term is quite small, so also compared to the scale, the gap is small, and then we have all the replicas, and it's formally simple problem. But then we can decrease the frequency toward the values of the kinetic term and the potential term. This means that the energy of the photons is comparable to the kinetic and potential energies of electrons. In this case, we are approaching a resonant regime, and therefore something more interesting starts to happen. In particular, in this case, we have a bigger gap, and in particular, we have a mixing between all the replicas, the band replicas. And this is due to the fact that we start to take into account of all the virtual processes of the electrons with the external field, which means that we take into account of more possible photons exchange, and they become more relevant in the calculation. So it's still an insulator, however, the system, and then we can decrease the frequency again. So in this case, in between the kinetic and potential energy of the electrons, and it turns out to be a metal. So it seems that we have found an insulator to metal transition, which is driven by the external field. And this is, again, due to the interaction with to take into account of all the virtual processes and the mixing of Floquet bands. Here I just represented this rho mode, but still we have, it has to be intended replicated in infinite times in the energy scale due to the net absorption or emission of photons. And still, even if we increase the Hubbard term, and in the static problem we should have a bigger gap around the Fermi level, here we instead still have a metal state. So we have the band dispersion which crosses the Fermi level. And this happens again if we increase more the Coulomb repulsion, so the Hubbard term. And this is true up to an upper limit. So some remarks, because we have computed this for Floquet quasi-energies, but of course a question can arise from this. So how real are them and what do they mean? So actually there are both some simulated experiments and some experiments performed. Actually the real experiments are quite few, because it is difficult to realize the experimental setup, because actually it is done for cold atoms and lattice of cold atoms, because all the theory, of course, is valid at 0 temperature. And here, however, we have simulated time-resolved photoemission spectroscopy, and we can see that according to the different, well, here the experiment is performed with 2 laser pulses. The first one, which is a pump, which has the role of the laser field and drives the system out of equilibrium. And then we have a probe, which is another laser field, which is instead which is used to probe the system, so to map the band dispersion. And it has a delay. And according to the delay, the time delay of these 2 pulses, we can see that how the Floquet quasi-energy bands form. And in particular, if they are, if the delay is too high, of course, we are not in the condition of having all the replicas and Floquet quasi-energy bands, but it's true if they are overlapped. So if we really probe the system when we are in the out of equilibrium condition. This is another experiment which has been performed on a 2-dimensional topological insulator, and we see actually also in lab all the Floquet quasi-energy bands. So this is the summary of the work. We consider the Hubbard model to take into account of the correlations between electrons, and then we extended this static model for correlated electrons to out of equilibrium systems in a non-trivial way, so using both Floquet's theory and the Hubbard theory plus the classical perturbation theory in order to describe the infinite lattice. And we got a tunable insulator to metal transition, and it depends, of course, on the parameters of the field, so both the frequency and the vector potential intensity. So this is the outlook. Of course, a lot of work can be done on this, such as, for example, an extension to higher dimensional systems, or the study of topological properties, which is non-trivial, by the way, and other studies. So with this, I end, and I thank you for your attention.
Okay. Thank you to Matteo. Are there any questions or? Okay.
So you also mentioned in your perspectives that one of the biggest perspectives is to extend this model to higher dimensional system, because of course most of the physical systems that you mentioned in the beginning of your talk are actually 2-dimensional and not 1-dimensional.
Yeah.
But as far as I know, like solving the Hubbard model, even without interaction in 2 dimensions, is a nightmare. Do you have any comments on this?
Well, actually, it can be done also on a honeycomb lattice, for example, on graphene. And using classical perturbation theory, it's not so difficult. Of course, you have to pay attention because, for example, for graphene, you have 2 sites which compose the unit cell. And so you have more problems because if you take a cluster formed by just 2 sites, it does not reflect the symmetry of your system. So you have to consider 6 sites, for example, so just an hexagon, and then you have to unfold the bands. But actually, it's not so difficult. It's quite straightforward once you have all this set of theories.
Okay.
As I understand, you mentioned that for a high number of configuration or hopping region, the electron tends to be frozen.
Yeah.
Can you explain this?
Yeah, when you have... okay, maybe I can come back. Okay, here. So, of course, when you consider the static Hubbard model, so without the external interaction, you have the kinetic term, which is related to the, let's say, tunneling probability of electrons to hop or to tunnel from one side to the neighboring one. and is related to the kinetic energy. But then you have the Coulomb potential, and it adds energy. So to the configuration, which is this one. So when you have two electrons with opposite spins on the same side. And of course, this favors this condition. When you have, therefore, a high value of the Hubbard term, this condition is so, let's say, not realizable, so it would cost too much for the system, so that actually the electrons prefer to stay on different sides. So in order to lower the energy. And so, of course, the system is, you can also see that in this way, to the system to be an insulator, because you do not have conduction at the end. So have I answered your question?
You didn't take in account the potential between the electron and the nucleus.
Sorry?
Potential between electron and nuclei.
Well, actually, in this, in this calculations in this model, you have, as you can see here, you use a local basis. So you already use electrons. I mean, first of all, you decouple the electron motion, let's say, to the nuclei with the Born-Oppenheimer approximation, and this is what you do usually. And actually, you take into account of the potential when you consider, for example, local basis. So the basis is localized due to the the ionic potential, let's say. So actually, you do. Okay. But you do not consider, of course, other interactions such as, for example, phonons. But you can still add them, not at this level. This zero temperature, let's say, calculation.
Okay, thank you.
Okay, we have time for just one question, but if it's not, we quickly move on because we're really late. Is there any other? Is another one who wants to make a question? You want? You can. You are allowed.
Sorry? INRiM functions. Yeah.
It's out of equilibrium limit. You made a limit for.
Oh, this one. Well, actually, it's related to the width, to the line width of the stage, of course, and it is related. I mean, here we take the limit of eta going to 0, so actually it doesn't matter. But when you have quasi-particles, you can have a finite lifetime, and usually this complex term at the denominator is related to the lifetime of this quasi-particle.
Just a quick one, just a curiosity. In your energy dispersion diagram, for example, if you terminate your infinite chain, where does additional states appear, if they do?
So if you have a finite chain, a truncated one.
Yeah, if you truncate.
Usually, I mean, you can have some edge states. So you do not, of course, if you have just a finite number of sites. Well, of course, it depends. First of all, if it is an open chain or a closed chain. But then you do not have, let's say, a continuous value for the wave vector. So you do not have just a continuous, let's say, dispersion. We just have energy levels. But in that case, you can calculate for example, the density of states, and you can see that there are there is a non-zero density of states which is localized at the 0 level, and these states can be localized at the edges, actually. Yeah.
Okay, thank you very much to Matteo Pugliani. And now we have the next talk is from Georgi Komeniki. that is from Tbilisi State University, and his presentation is parametric resonance-induced chaos in magnetic damp-driven pendulum.
Okay, hello, my name is Georgi Komeriki. I'm the first year student of bachelor's in Tbilisi State University. And today I'm going to present parametric resonance-induced chaos in magnetic damp-driven pendulum. I was working on this problem in 2015 while I was participating in IYPT, International Young Physicists Tournament. So this was one of the tournament's problem. And after that, I continued my research and published this paper in Physics Letters A. So let's begin. So the problem is the following: we have a pendulum with in the end of the pendulum, in place of the bob, there is a magnet. And this pendulum is able to swing in 2 dimensions, and just below the pendulum we have a solenoid where an alternating current flows through it. So my goal was to examine this model. So now, firstly, here is a plan of presentation. So firstly, I'm going to explain the phenomenon. Then I will write down theoretical model about parametric resonance. Then I will write down and have equation of motion. Then I will make some chaos analysis and prove that the system under certain circumstances is chaotic, and parametric resonance is a necessary condition for chaos to exist in the system. So then I will show you some experiments, and of course compare experiments with the theoretical model and numerical simulations and calculations which I made using MATLABs, and in the end I will make conclusion. So now explanation of the phenomenon. So we all know what the usual oscillation of the pendulum looks like, right? But if there is a solenoid just below this pendulum, and then direct current flows through it, and the solenoid always attracts the magnet, the motion will look approximately like this, yeah? And if the solenoid always repulses the magnet, the direct current flows through it, the motion will be looking like this, yeah? But in our case, what happens? An alternating current flows through the solenoid, and it sometimes attracts and sometimes repulses the magnet, so it's a little bit cumbersome, and that's what I'm trying to just work. So just for more, I will show you this experiment to be clear what we are talking about. So it's like this. So it starts just random motion, and yeah. So let's move on to the originality of the problem. So this is a particular case of chaos when the chaos is induced because of parametric resonance, and the particular case of parametric resonance induced chaos. So it's not really special, but the originality of this problem is that I considered the dipolar momentum of the solenoid to be vertical. So this system was examined before by Dubushinsky, in case when the dipolar momentum of the solenoid was horizontal, and in that case he got some other interesting phenomena like quantization of amplitudes, but in my case I get chaos and parametric resonance. So I will move on to this case. So let's start theoretical model. So first assumption is that we just assume that both solenoid and magnet in place of the bob of the pendulum are point-like dipoles. So here from point the magnetic field from a distance r from the center of point-like dipole is the following. So the second magnet, the magnet is so the solenoid is only at one place, and the magnet is just moving in different directions. So the dipole-dipole interaction energy will be the following, and the magnetic forces acting on this pendulum and magnet of the at the end will be the gradients of dipole-dipole interaction energy, respectively Fx and Fy forces. So we write down then a equation of motion, but in case when we consider the deviation angle alpha as a small one. So when we just write Newtonian second law on tangential axis, we will get this following equation, and after just denoting the constants, so the dipolar momentum of the solenoid changes with time, and we denoted some combination of constants by h, and this is a differential equation that we will get. And if you look at it, it's just a Matthew equation. I just added friction. So we seek for the solutions in this form as S is the growth rate, and we get that S should be the following. And for the S to be positive, for this to be correct, S should be positive, should not be imaginary, should be real, for the parametric resonance to exist. And for that, this H should be more than this. The frequency, driving frequency, natural frequency, this is the friction coefficient. And I measured friction coefficient and dipolar momentums using experiments. So now let's move on. Now we want to write equation of motion, so the whole motion, not only in the case when the deviation angle is small. So we do the same. We write down the dipole-dipole interaction energy, derivate it over x and y coordinates, and get the following differential equation. And this fx and fy forces are not written down because of their cumbersomeness. So, I believe that the differential equation cannot be solved analytically. So I solved it using MATLAB. Now what are the results of theoretical model? So sometimes you get that it is not chaotic and it performs some oscillations. Sometimes we get that it's chaotic, but when there is a parametric resonance, for example, from a very small deviation like this, this pendulum is able to gain large amplitude. So that's a parametric resonance from a very small insignificant initial deviation. The system is going to large amplitudes, and sometimes there's parametric resonance, but because of the friction, the system is not able to gain large amplitudes. And now let's move on to the proof of chaos and prove that parametric resonance is necessary condition for chaos to exist. So we just so what should we do? Like we can plot the graph of angle dependence on time. So and we can change some parameter insignificantly, like the angle, and to just plot another graph. It's like we changed it for 0.001 rads. So if if the difference between these graphs increases exponentially within the time, then there is parametric stability, but and there is possibly chaos. So this is what I did, and this is the case this is the case of my system. I just put these equations in MATLAB, and this is what I got. The blue is corresponding to blue curves corresponding to the difference of alphas between alphas in two different conditions, and this red is corresponding to angular velocities. Just it's divided on the initial difference because I wanted to place both graphs on the same graph, and just shows that there is exponential growth. Yeah, in the beginning, so we have on y-axis there is a logarithmic scale, and there is a linear growth in the logarithmic scale, and we can say that it's exponential growth. So and theoretically, we found out theoretical growth rate is 3.63, and we can calculate Lyapunov exponents, mean time Lyapunov exponents, and compare it with theoretical growth rate. So for this case, in this area, the Lyapunov exponent is 23, and it clearly does not match it. But in other areas, it is 3.5. And I believe that this error is caused because of the fact that this current, when current starts to flow into the solenoid, in my theory, I say that the force starts to act on the magnet immediately. But it's not really so. And so I tried to just prove this point, my belief that I multiplied the dipolar moment onto a smooth function, and so that when that force does not appear immediately, the theoretical growth rate matches with Lyapunov exponent. So I said that during my calculations and just comparison of Lyapunov exponents with theoretical growth rate, I did not take into account this beginning of the part, so half seconds. My theoretical model was about small, the equation which I solved analytically was for small angles. And for small angles, for small initial angles, the theoretical growth rate matched it with Lyapunov exponents. But if the initial angle is very large, they don't. Because the equation was solved analytically for small angles. So, and we get this following this Lyapunov exponent as theoretical growth rate. So now we move onto the main part. This is boundary between chaos and stability. I said that when there is parametric resonance, there is chaos. It's a necessary condition. Why? So, this H is denoted, these constants are denoted by H, and we get when their H should be more than this for the system to have parametric resonance, or the parametric resonance to exist in the system. So H is dependent on initial distance R from Bob to the solenoid, initial distance when the deviation angle is 0, and this blue curve corresponds to the air dependence on driving frequency. So this blue is the boundary between parametric resonance and not parametric resonance. But from MATLAB, the equations of the motions which I wrote in MATLAB, I found out what was the boundary between chaos and stability. And these are red dots. And these error bars correspond to my experimental results between the boundary between parametric resonance and chaos, so that I can say that they matched perfectly, and I can say I say that when there is parametric resonance, the system is chaotic. When there is not, the system is stable. Not chaotic. I proved I plotted these red dots, and for the chaos to be in the system, I say that it should have the difference between within time should increase exponentially, and the Poincare map should be like this. So this is the case when the system is chaotic, and the closed trajectory is when the system is not chaotic, and the interval within the of plotting dots was the own oscillation frequency of the pendulum. So when this oscillation is periodical, and when there is no magnetic force, the Poincare map will be just a point. And let's move to the last part of my presentation, experiments. So I had to compare experiment with theoretical model, so I rewrote this equation of motion to the physical pendulum. So only just some coefficients changed, and I can show you that. So experimentally, there is an error, and the initial deviation of the pendulum is 0. But because of the fact that we have errors in experiments, it's something, yeah. And when we turn on the magnet, when we let the current flow into the solenoid, yeah, from the 0 deviation, it starts oscillating and this kind of chaotic motion. So, yeah, this is a two-dimensional model. I think that it's enough. So now let's move on to the comparison of theoretical model and experiments. Of course, I could not compare theoretical graph motion of the graph with experiments when there is chaos in the system. So I compared them when there was not chaos, the system was stable. So for these given parameters, I measured, of course, friction coefficient and dipolar momentums with experiments. For these parameters, we should have the oscillations like this. This blue line is blue curve is theoretical curve, and red dots are plotted from experiments. So I recorded the video and just for us some time, for some intervals, I plotted these dots on this graph. And there is an error in the beginning, and in the end it increases because, and that's error I think that is because of my assumptions that I made an assumption that they are point-like dipoles and so on. This is a comparison, and it's okay fitted, I think. And now, yes, the conclusion. So we have proved the existence of parametric resonance in our system. So when there is a parametric resonance in the system, it's always chaotic. Parametric resonance is investigated for small angles analytically, and for large angles, I studied that equation using MATLAB. Lyapunov exponents were calculated and compared to theoretical growth rates. Theoretical results are compared to experiments, and and of course friction influence is estimated both theoretically and experimentally, and other parameters were just calculated experimentally, and we have solved the part of the problem which had not been solved before. So here are the references, and thank you for your attention.
Okay. Thank you to Georgi Komeriki for your presentation. We have time for one or two questions. Are there any questions?
Do you have not experimental data for the chaotic region?
Experimental data for what?
In the chaotic region of your...
I have not compared this. I couldn't compare theory with experiment because, for example, when there is a chaos, so I can find out theoretically what is the motion like, but because of the experimental error and because of the fact that when there is chaos, an insignificant change just changes everything, I could not compare it. But what I compared from experiments is that I found when the system just becomes chaotic. So I said that, so I proved theoretical that parametric resonance is a necessary condition for chaos. And from experiments, I saw for which parameters the pendulum started to oscillate, gain large amplitudes from the zero deviation from the initial point. And I said that there is parametric resonance and there is chaos. So in chaos, I have on this comparison.
Okay, thank you.
It's okay. It's almost the same question. I mean, how big are the error bars in this graph exactly for the border between chaos and stable? I mean, if you put a value of the frequency exactly on the red dot, and for the error value, how stable is your pendulum?
Actually,
how decide between stable and chaos?
Actually, the error, unfortunately, is quite large. Because I couldn't do the proper experiments to reduce the error, but I think that physically it matches really well with the theory. And to just say a number, I think that, for example, for the given parameters, when the parametric resonance should have occurred for the 20 Hertz, driving frequency, the margin of the error was from it occurred from for example from 17 to 23, like that, 10% probably for experiments,
Okay, thank you very much for your interesting presentation. Now we are moving we're going on with the next talk. Here you go. Okay, it is from Stefano Marcantoni. It is from University of Trieste. Thank you very much.
Okay, as you can see from the title, I'm going to talk about the thermodynamics of a bipartite quantum system, and in particular, after a brief introduction to the topic, I will show how we can formulate a generalized version of the first and second law of thermodynamics for these bipartite quantum systems, starting from the exact microscopic dynamics, and in such a way that the very important role of correlation between the two partitions is highlighted. Finally, I will conclude summarizing the key points of my discussion. So, I'm a PhD student, and my current research deals with quantum thermodynamics that, roughly speaking, is the study of energy and entropy exchanges in quantum systems. As for standard thermodynamics, the original motivation for quantum thermodynamics is quite practical. Indeed, already in 1979, Alitsky published the theoretical model for a quantum heat engine. And in the last decades, with the advent of nanotechnology, actually there have been a lot of these publications regarding possible applications of quantum thermodynamics. But I have to say that I'm a theoretician, and I'm mainly interested in some kind of more fundamental questions, as to say equilibration and thermalization in quantum systems, or also the emergence of the laws of thermodynamics from the exact macroscopic dynamics of composite quantum systems. And indeed, in what follows, I'm going to talk about this second topic. So, this is the model I'm going to consider. We have a closed quantum system that I call SB, and this is composed by two interacting subsystems, S and B, of course. I consider an initial product state. I hope that most of you are familiar with the theory of density matrices. By the way, briefly, you know that for a closed quantum system, a pure state is described by a vector in a Hilbert space. The density matrix related to this vector is the projector, psi, and a generic density matrix is a convex combination of these projectors. Basically, it is a linear combination, and the weights of this combination are the probabilities that the system is in one of these possible pure states. So, this is the form of a totally uncorrelated initial state for the system SB. We consider a time-independent Hamiltonian for the total system, and this Hamiltonian is composed by three parts. The first one that acts only on the Hilbert space of system S, the same for B, and there is an interaction Hamiltonian that couples the two and acts on the Hilbert space, that is the tensor product of the Hilbert space of S and the Hilbert space of B. We can get information about the each of the two subsystems by means of the partial trace, that is nothing than integrating the irrelevant degrees of freedom. What about the dynamics? The dynamics of the global system is given by the Schrödinger equation. I don't know if you recognize it, but this is essentially the Schrödinger equation written in the language of density matrices. We can describe the dynamics of any of the two subsystems using, again, the partial trace. And let's comment on that. We see that this kind of equation, number 2, is kind of different with respect to equation 1. We see that there is a first part that is similar, a commutator with an Hamiltonian, but there is a further term. This further term is very important because actually, in general, the dynamics of an open quantum system, because both S and B are open quantum systems since they are interacting in something else, this dynamics in general is really different from the Schrödinger dynamics because it is not unitary. This means that pure state can become proper density matrices in time. And this is very important because this gives you the distinction between, let's say, the classical and quantum setting. In classical physics, if you have a pure state that is a point in phase space, and you consider only a subsystem, this subsystem will be described by a point in the reduced phase space. While, if you consider a quantum system and a global pure state, in general, this pure state will remain pure because it will evolve by means of the Schrödinger equation. But if I take the partial trace and I consider only one of the two subsystems, then I will not find a pure state in general. So this is really a strong difference between the classical and quantum case. We have essentially an objective lack of knowledge due to the correlation between the two subsystems. More specifically, you see from here that we have defined this chi of t that is a quantifier of the correlation between S and B, because it's the difference between the full density matrix rho of t of the global system and the tensor product of the two marginals. And we have defined also this effective Hamiltonian that is not simply the free Hamiltonian of S, but it contains a correction due to the interaction with the environment. Okay, maybe I can skip these details. Briefly, using this effective Hamiltonian that we find in the dynamics, we can define an internal energy for both system S and B. I put only S here, but you can imagine the same for B. It's exactly the same. And we see that if we compute the difference between the total energy and the sum of the two subsystems energies, there is a missing quantity. There is really something, kind of energy stored in the correlation between the two subsystems. You see from the last equality of equation 10, indeed this term is due to the interaction Hamiltonian, the effective interaction Hamiltonian, that is the difference between the total Hamiltonian and the two effective Hamiltonians, and the quantity of correlation between the two subsystems. So now we have the energy for each subsystem. In thermodynamics, usually one distinguish between work and heat. And in this case, we can do it in a very natural way because we can separate the two contributions to the energy variation. One of the two is given by the derivative of the Hamiltonian and the other one by the derivative of the density matrix. Why is this reasonable? Basically, you see that in a scenario similar to one of the previous talk, in which you have a time-dependent Hamiltonian, but no interaction with an external quantum system, you have that the second term is 0. Okay, maybe it is not evident, but you can use the cyclicity property of the trace and the fact that the evolution is given by the commutator with a between h and rho, and you see easily that dq is 0, while you have a work given by your external field. Instead, if we have a time-independent Hamiltonian, but a system interacting with an external environment, maybe a thermal equilibrium environment, you have that the first term is 0, and the second one is non-zero, due to the non-unitary part of the dynamic equation. So basically, with the previous definitions, the first law of thermodynamics is identically satisfied, but we have more. We know that we have two separate balances of heat and work, and we see that while dWs is equal to minus dWb, we have a contribution of the correlation between the two subsystems in the heat balance. It's something like, you can imagine this correlation acting as a third subsystem that can exchange heat with both S and B. And this is our first interesting result. What about the entropy? We can use the von Neumann entropy to generalize the thermodynamic entropy for any kind of quantum state. So there are no hypotheses about thermal equilibrium or something like this. And this von Neumann entropy has very nice properties. In particular, the von Neumann entropy of a non-correlated state, of a factorized state, is the sum of the two entropies, while if you have in general a correlated state rho, you have that the difference between the sum of the two entropies computed with the marginals and the entropy of the true density matrix is always non-negative. This is called subadditivity of the von Neumann entropy. And the quantity that you can define is the mutual information. You can define as in equation 18. And this characterizes the amount of total correlations, that means both classical and quantum, shared by the two subsystems. If we consider that the initial state is uncorrelated, that was one of our hypotheses, actually the only one, and since the total entropy is conserved because the Schrödinger equation of the global system preserves the von Neumann entropy of the total system, we see that when we sum the entropy variation of S and B, this quantity is always non-negative. It's always greater or equal than 0. And again, you see the fundamental role of correlation here, because if the dynamics does not build correlation in time, then this quantity will be identically equal to 0 for any time. Of course, this is not the end of the story, because you can say, okay, this is a statement valid only for finite time differences. One would like to say something more, maybe to say something about the increasing of entropy, something like an infinitesimal statement, a differential statement for this second law. And in order to do that, we have to make some more assumptions. That is, when we consider a small quantum system interacting with a large thermal environment at a certain inverse temperature, beta, in case of weak coupling, so under some particular conditions on the interaction, we can find that the dynamics of system S is given by this particular equation that in the theory of open quantum systems is known as Limnad equation. And you see this particular structure, you have, again, the first part, that is the unitary part of the evolution, Then you have the last term, that is an anti-commutator, and this anti-commutator usually you can find it in, for instance, in some kind of effective dynamics that describes decay of particles, because you can group it with the commutator and it behaves effectively as a non-Hermitian Hamiltonian. But there is a further term, that is this Vk rho s Vk dagger, that is responsible for the mixing. That means this is the term responsible for transforming pure states into statistical mixtures. Of course, in general, this kind of dynamics does not preserve energy, neither entropy. In this case, we can say something more. Indeed, already in the late 70s, both Alinsky and Spohn, and also Lebois, I think, they proved that this kind of differential statement of the second law, that is, if you define the effective irreversible entropy production rate in analogy with the classical case, that is, taking the difference between the total variation of the entropy and the heat flux in the bath, this quantity is always greater or equal than 0. This is a very strong statement, but of course you have to impose that your evolution equation has this particular form, the one that we have seen before. So to conclude, we have seen that in general energy and entropy are not extensive if considered at microscopic level. But using suitable definition for various thermodynamic quantities, it is possible to formulate the first and second law of thermodynamics, or at least a generalized version of these laws, for a bipartite quantum system, starting from the exact microscopic quantum dynamics. And moreover, this formulation highlights the very important role of correlation between the two partitions. So, if you are interested in this kind of topics, you can find this and also something more in a recent paper that I've written in collaboration with a group of Professor Ali Rezakani at the Sharif University of Technology in Tehran. And actually, when I was writing this presentation, it was only on the archive, but last Friday it has been published on Scientific Reports, so now you can find it on the review. And that's it. Thank you for your attention.
Thank you for your presentation. And now we have time for 2 questions. Are there any questions? Any suggestions? Comments?
Do you think about some practical system in which you can test this?
Well, usually in this framework of, let's say, quantum thermodynamics, one consider very simple system because you have to allow for a high degree of control. Basically, one consider few level atoms interacting with laser, or optomechanical systems, or again cold atoms in optical lattices. These are the main real physical systems.
Another question? Okay, thank you very much for your presentation. And now we're going on with the awards ceremony, but I can see Alessandro. He was here, and I don't know where he is. I can't. Okay, Alessandro is here with us.
So we made it in the end. Now the schedule is we have a very brief award ceremony and then the closing remarks. So I need here on the stage the two guys from the LOTQD, the sponsor which permitted to organize this award. It's a poster award. We have to say we formed a commission with local and permanent organizing members, and all the posters got very good evaluation. And but I would like that our sponsor call the winner, because it's the suspense is now, it's coming, but no, because it's just symbolic. I repeat on the behalf of the organizing committees that all the posters and the talks were very high level, and so please. We have another one.
So now we need I need the name. I need.
So we can do that.
Oh. Okay, Francesca Rolle.
I don't know if we have some certificate, symbolic. Where is the envelope? Where is Silvia? Maybe she's coming with the envelope. Okay. So, okay. In the middle, I would start. Please stay here.
Yeah.
Okay. We wait for the envelope, and it's coming. Please make photos. No, photos. Stay there, still.
Thank you for the prize. But I would like to special thanks my colleague Enrica, because she did a huge part of this work. So the prize is also for her.
Obviously, the co-authors of each poster didn't evaluate any poster they were involved in, so there is no bias. Now we have some number here. We have been 80 people, and from 50 countries, and 32 talks, 34 posters, 10 observers, 3 invited lecturers, Elisa Palazzi, Andrea Giacchero e Fabio Sciarino, not in order, 1 lectio magistralis, Walter Bick, and now I have another list. I hope no one will be missing. Please correct me if I miss. I made a mistake to let you do it. No. So, first of all, the president of the institute, Diederik Wiersma, and the vice president at INRiM, Aldo Godone, the director, the administrative director, Ines Fabbro, scientific director, Maria Luisa Rastello, and all the scientific council, committee, the scientific council, Marco Genovese e Paola Tiberto, internal members of this scientific council. All the administrative personnel that you don't see here, but they worked a lot, in particular Elisabetta Melli, and the sponsors are Calref. Maybe we can open the website with, thank you. The sponsor covered something like 40% of the budget. So thank them in particular for the social dinner that you will remember, I think. And so Calref, ID Quantique, Teledin Lecroy, Anton Park, Risiel Instrument, Pfeiffer Vacuum, Sistemi HS, and Lot Quantum Design that you now well know. Then some people in particular helped us with different technical, practical problems or ideas. So Giancarlo Cerretto, in particular for the streaming part of the meeting, Sandra De Nasi for the network and all this audio stuff, Gianpaolo Scialpi for photography and other issues, all the Paolo Cattaneo too for the technological part, and all the responsible for the laboratories that we are going to visit in the last part of the conference, the lab tours that you picked up and you chose. In the end, I want to have here the permanent organizing committee and the local organizing committee. So please come here. And so, not in order. So not in order, but in alphabetical order. But I don't know which is present, so not in order. Fabrizio Piacentini, Giordano Cattani, Marco Di Stefano, Emanuela Pusceddu, Marina Migliaccio, Matteo Serra, Alessio Avella, Enrica Pessana, Lapo Lolli, Raffaella Romeo, Rugiada Cuccaro, and the person without whom practically nothing would be possible, Silvia Cavallero. Come here, Silvia, please. Oh, Enrico Simonetto.
È imboscato dietro.
No, è giusto. And finally you. Thank you for your participation, for the high-level contribution, and we kept in time all the schedule. It's very good, very good. Thank you very much. So now we can, I think we have remarks from the permanent committee, and then we can go to the lab tour. If anyone wants, yes, we have the attendance certificates, but you can take before leaving at the end. So, please.
So we miss to thank Alessandro Gultrera. And so on behalf of the Permanent Organizing Committee, I want just to tell you that we are organizing the next meeting, because when one meeting ends, you have to start to prepare the next one. And next year we will be in Cagliari. So we are now fixing the first details of the organization, so looking for sponsors and people, local people, to take care of organizing everything. And then I want to ask you if you have any idea, if you want to propose some idea for the meeting of 2018, so the 9th young researcher meeting. So if you have any idea, if you want to propose your institution in Italy, in Europe, please come to us and let us know that you want to do it. And we will help you with our experience, and we will make it maybe possible. So to finish, I want really to thank the institution, the INRiM, all the people here working every day since the first morning, and all the speakers, all the contributors to the meeting, and all the members, my colleagues of the Permanent Committee. Thank you.
Before we forget this, we will stay in contact for the publication of the proceedings. It doesn't finish here. In which way? You say that. Let's stay in contact, and the provisional deadline for proceeding submission is the 20th of November. We will send instruction around, but please do write to us for any question. And finally,
okay, we are the Permanent Committee is now founding an organization. The what's it called? EMP is International Physics Network. We have just started a website, and we are collecting registration to the organization. So if you want to be part of it, just contact one of us. The idea of the network is, the organization is to create a link, a bridge between the students, the PhD students, or the one that already have a PhD degree, with the world of the academics, and with the world of industries and society that want to have you as workers, the workers of the future. So anyone wants to add more information?
Okay, after these nice speeches, I have to remind you that for the lab tours, you have to reunite upstairs. Every one of you has a color and a number. You will see some flags with the same color and the same number. Just reunite under those flags, and somebody will guide you through the tour of this sort of. And if somebody wants to visit and didn't register for it, he can just choose on the fly and do it now, because otherwise, okay, you'll skip this chance. And anyway, if at the conference dinner there had been the prize for the best drinker, we all know who would have won that. Stand up, best drinker.